Should be live just... No. Okay, I think I'm live. Hello, wonderful people of the internet. Welcome back to another episode of Leos Labs. So today, I'm going to do something that I don't... Look, I have consistently said I do not want to do this type of stuff on stream. It's not necessarily because I don't like the stuff that I'm doing. It's that the particular project that I'm working on right now is incredibly sticky, and it's very difficult for me to describe what I'm doing while also doing that thing. So what I'm going to do in the background is I'm just going to go ahead and start some tests. So let me go ahead and CD into projects, CESMIX, Molly, and I'm going to run Julia --project. And then we're going to do -T12 for 12 threads, and I'm just going to run test, okay? Now, while this is running in the background, I want to talk about what I'm doing. So for the past few years, I suppose, I've been working for the CESMIX project at MIT. Now, let me explain what I'm talking about. So let's go to General PP and let's talk. So CESMIX, I don't remember what it stands for, to be honest. It's like Center for Exascale Simulation something mix. I don't really know what the materials and IX. I don't know what it means. You can Google it. I'm sure you can find it. It's not like it's like a secret project or anything like that. I've been working for this project. In particular, my job was to do GPU molecular dynamics simulations. Now, what are GPU molecular dynamic simulations? What are these? So a molecular dynamic simulation is essentially the simulation of a bunch of particles in space all bouncing together and hit each other, right? That's essentially what it is, right? So you have a molecule, a particle here, a molecule, a particle here, a molecule here, a molecule here, a molecule here, right? They're all interacting with each other, right? By some force law. So we have these guys all interacting with each other, right? So they have some network where they're all kind of, you know, touching each other and like forcing each other to move based on those force laws, right? This, I guess, another connection here that I missed. Now, because we have all these particles interacting with each other, basically with F equals ma, we run into a situation where we have this like n squared scaling, right? So basically every particle you add in like changes how this simulation runs, because it has to interact with every other particle. So n particles have to interact with n other particles, so it's n times n, which is equal to n squared scaling, right? Now, that's not particularly great. You can speed it up with GPUs. There's a bunch of different ways to speed it up with GPUs, and I've done, you know, GPU molecular dynamic simulations for a long time. So for the CESMIX project, I was expecting to just jump in and kind of do the same thing. And so I was working on a project that was called Galilee, okay, at the time. It was actually for... it was for galaxy simulations that I had repurposed for this particular project. I don't know if you guys remember, a few years ago, I was doing a 4-dimensional galaxy simulation, and basically the project turned into what I was doing for MIT. Now, what we realized was, look, I have done MD GPU simulations for, look, I've done this many times. It's not new to me. But it's probably better for us to interact with pre-existing software than for us to build our own software solution that might already exist elsewhere. So let's talk about other software solutions. There's LAMMPS. LAMMPS is a well-known molecular dynamics engine that pretty much everybody uses for this particular thing. It is the state-of-the-art for MD simulations, and it does have GPU capabilities. It uses OpenCL for generic support and has specific CUDA modules for pretty much everything else. Now, what we've done in CESMIX, what I didn't do, one of my friends did, is they have added a .jl. They basically allowed people to call LAMMPS from Julia. Okay. Now, there's yet another project called Molly. Molly is a molecular dynamics engine in Julia. Now, the name is probably just because Julia is like a feminine name and Molly is also a feminine name. And so if you put it together, I guess just Molly and Julia kind of work together. But Molly.jl is a package that is used to do molecular dynamic simulations. So we said in the CESMIX crew, here's what we should do. We should take Molly, this pre-existing software, and we should modify it so it runs heterogeneously on all GPUs, right? So it can run on AMD in particular, but it could also run on Metal, and it can also run on Intel, and it can also run on everything else, right? Because that's what I can do. That's a unique power that we have in the Julia ecosystem that I'm very capable of doing, right? And so a few years ago, I put in a PR to provide AMD support for Molly.jl, right? And then I'm not going to say that there is any drama here, because there is not drama, but what ended up happening was this PR it wasn't rejected, but it was not submitted in. And the reason it wasn't accepted was because we were fundamentally missing there was one test that failed, right? In particular, we missed this function for accumulate for AMD GPUs. Now, accumulate, if you guys know, is like a parallel summation type of thing. What it does is it adds vectors together and adds them together again and again. So basically, like if you have a list of numbers, like just a list of ones, 1, 1, 1, 1, 1, accumulate, what it will do is it will add all the ones together. So this is, let's see, 1, 2, 3, 4, 5, 6. It'll be 6, 5, 4, 3, 2, 1. I think. It's something like this. It essentially will add all of the ones together here, and then less ones here, and so on and so forth. So that functionality didn't exist in AMD, but it did exist in CUDA. So what did we do? We did not have this functionality, and we said, okay, well, what should we do? In an ideal world, here's what we're going to do. We're going to update the GPU arrays package, dpu.jl arrays package. This is the package that is like underlying all of the GPU ecosystem in Julia. That is how we get the ability to dispatch GPU kernels to like varying backends, right? I've said before, like, you know, when it comes to lower level code for GPUs, there's kind of like this, there's LLVM, and then there's like SPIR-V, and then there's all these LLVM like dialects that depend on the hardware, right? So for NVIDIA, it's like NVPTX. For anything you're using with Vulkan or OpenCL, it's going to compile down to SPIR-V. There's like its own special thing for AMD. I don't remember what it's called, but it has like a different naming convention. I don't remember. But the fact is that when you're writing code, it boils down to this lower level representation, and the ability to do that in part comes from GPU arrays, in that it allows us to do multiple dispatch and allows us to kind of point the GPU compiler in the right direction to get the appropriate output from the appropriate package, right? So it's a way to do that, right? And so we said, okay, well, let's add accumulate to GPU arrays.jl, but there was a catch. See, the catch was that GPU arrays had its own DSL, domain-specific language, that was different than the rest of the ecosystem, right? Rather, there was not a domain-specific language that the rest of the ecosystem had really founded or like had coalesced behind. And unfortunately, this DSL, at least for me, was a little bit too complicated. I couldn't quite figure out how to implement accumulate in that DSL. So we had the idea. How about we modify that DSL? So instead of using the DSL we had before, let's use kernel abstractions, which is a well-known API that a lot of people use in Julia to write generic GPU code, and it already has existed for a while. People are quite familiar with it. People know how to use it, and this would allow us to not only implement accumulate, but a lot of other functionality that did not currently exist in GPU arrays we could implement on the kernel abstractions layer. So that's what I did. I spent a long time, like months and months of effort, making it so kernel abstractions was now the foundation for GPU arrays, right? And that was all so we could implement accumulate, so that these tests would work in AMD and all these other tests up here, right? And so I did it. It took a long time to get this done. It was like, I don't know, months, maybe even a full year of work on this thing. Not full-time effort, but it was like kind of like consistently working on this thing for like an incredibly long time, like off and on over the course of a year. So I got that done, right? And then at the end of the day, I'm very ashamed to say that by that time, Molly had changed so much that we no longer needed the accumulate function, and we didn't need any of that functionality that I spent like a full year on. That's fine. It's okay. I don't mind. CESMIX was happy because at the very least, we can now say that our project has directly contributed a significant amount to the Julia GPU ecosystem, which we could not have said before. Like now we can say that. And, you know, as a Department of Energy project that wants to see sustainability for like, you know, software engineering in the future, fine, fair enough, cool. It's okay. It wasn't like it was a waste of time. It's fine. This helps out a lot of people. It's okay. But the problem is consistently, like the Molly.jl package, the change that I did for this, I actually had to do again and again and again. So not only did I have to do it once, but I had to do it, I had to do Molly.jl with kernel abstractions now, because before it wasn't a kernel abstractions backend, I just had switched out like an array type. So then I did Molly with kernel abstractions. I did this not once, not twice, but 3 times. I think maybe 4 times, to be honest. It was basically the same changes I did in 4, but every time I changed the code, something else happened in the background. Like, for example, they implemented CUDA-specific kernels that used warp-level semantics, and warp-level semantics, for those who don't know GPU computing, it's one of those things that is really NVIDIA-specific right now, just because, well, even the hardware doesn't really do well at differentiating like individual threads. A warp, for those who don't know, is like a it is the minimum level of parallelism available on the GPU. So usually it's like 32 or something like this, and that is to say it is the smallest step you're allowed to take on the GPU. So 32 threads must execute in parallel at the smallest scale, right? For NVIDIA hardware, it's possible to do like individual thread indexing, which is what they're using for this kernel, but it's not always faster, and you have to really think about why you're doing it. Regardless, that was something we didn't have in kernel abstractions because it's CUDA specific, and kernel abstractions is for everything, right? And there's a few other things that we didn't have, and just over time it ended up being, you know, I would implement something, it'd get shot down. I'd implement something, it'd get shot down. I'd implement something, it'd get shot down consistently again and again and again and again. And so overall, like I've been spending basically the past 2 years consistently writing code that doesn't get merged, but it also is not shut down. And people are like, we'll just leave it here because it is a good idea, but we don't have time to review it. And that's just where I've been for the past 2 years. Chocolate Mints, bye. Hi. I said Chocolate Mints, by the way, hi, how are you doing? Anyone else who might be lurking in chat, hey, thanks for being here. So this is where I've been for the past 2 years, to be honest. And, you know, it's back in the day when I was working at MIT, like at MIT campus. I'm still working at MIT, but when I was like on the campus and I wasn't working remotely in Barcelona, I had more time. And part of that is because I didn't have a kid. And so I was able to manage like software engineering projects unrelated to the MIT project, as well as doing the MIT job. Even though the MIT job spent like, I spent like 80 hours a week doing that, I was still able to find extra time because I was willing, I had the time to work. Nowadays, I don't have that time, right? Like, in part, it's because I have a child, and to be honest, this child is not sleeping through the night. To give you an intention of a normal night, I will give you what last night was for me. He went to bed at 10:30. I know what you're saying. You should be able to put your child to bed earlier. Look, if you have a child, you'll understand. That's not even theoretically possible, right? So he went to bed at 10:30, right? Woke up a couple times, so we'll say roughly 11 is when he was actually sleeping soundly. Woke up again at 4, right? So that's 5 hours of sleep, and was up from 4 to 5, and then went back down around 5:15, and then woke up again at 9. So if you're counting up the hours, it's roughly 5 hours plus another 3 to 4 hours, so 9 hours of sleep, right? Split between 2 sessions, right? Now, obviously, that means that my theoretical maximum for sleep is 9 hours, and you don't get your theoretical maximum, right? Like last night, I was working till after midnight because I just had to catch up on a bunch of different things, and so I got maybe 6, at best, when you add it all together. And this has just consistently been where I've been at for the past couple of years. I don't have time. And because his sleep schedule is so bad, we can't get him in daycare until 10:30, 11. And so for today, I could not start working until noon. That was it. That was the earliest I could start working. And I have to stop working at 4 because I have to start making dinner. So what I'm trying to say is I have 4 hours of good work per day. That's it. That's the maximum I can allot. Sometimes I can get up to 6 if I'm really if I'm really focusing, but it's impossible to get 40 hours of work done with a small child. I don't know how other people do it. It's just not possible, right? And so the reason this has been frustrating is not necessarily because the software engineering project has been kind of stalling and going back and forth. It's because literally all of the time I have to get work done has been spending not doing research, but instead just kind of going back and forth on these PRs that are ultimately not meaningful. You know what I mean? Like this accumulate thing ended up not being particularly useful. This Molly kernel abstractions thing, I mean, look, it's useful. Like there's going to be people who use it, but actually the CESMIX group, they're more than happy using lamps.jl. So I'm sitting here kind of like, what am I doing this for? Like there's no one that actually needs this in our group. People are more than happy to use lamps, just the lamps backend that we have for Julia. We've already contributed to the Julia ecosystem, and now I'm just like, what is this? What is the reason that I'm doing this? Like, is it for money? I'm okay for money right now. I don't need to just be wasting my time to get dollars. I need time, not money. You know what I mean? And so it's like, this is where I've been for the past year, where it's like consistently I want to do more work, but I have no time to do that work. And that's been the frustrating part of this. And so when we're talking about my latest failure, which is what I named the YouTube video and stuff, I'm talking not necessarily about how there is a specific failure that is happening right now that I need to fix, but I'm also talking about how I have failed to allocate my time appropriately to allow myself to finish projects that I'm actually passionate about. And as someone who is very driven by the desire to do new research, to do new things, it has been not like, it hasn't led me down like the path of depression or anything like that, but it's been very frustrating to do. And I will also say one more thing in that, just the other day I was working on a couple papers. Like I finished 2 papers this past month, right? One was for triangular matrix methods and stuff like that. And it's just, I don't know, the act of writing a paper was just so eye-opening. It was so much more fun than like literally anything I'd been doing with the software engineering so far, that it was like, man, that's what I want to do. Like I want to do new things that people haven't done before. And that is again why I'm streaming, because I have, been going back and forth as to the absolute best way I can present this research so that the most people understand. And I do understand that like streaming does slow down that process significantly. But on the other hand, it should, we as researchers need to do a better job of openly communicating the research that we're doing. And this is part of the research I've been doing. It's you could argue maybe not research, it's more research software engineering, and that's probably fair. But certainly this has contributed a lot to research that other people have done. Well, maybe not as much as I'd like, but this is, in a sense, the best I can do for research at this point in time. Now, there will be more like definitive research projects in the future, but for now, it's not. Right now, this is where I'm at. I need to finish up the MIT work before moving on to the other stuff, and there's one last thing I need to do. So let me go ahead and pull up the PR. And again, guys, if you have any comments, questions, concerns, ideas, anything like that, feel free to let me know, and I'll totally address it as soon as I see it in chat. So let's go to Molly.jl. All right. So guys, I'm going to jump scare you guys. I'm so sorry. Let me go here to kernel abstraction support. And let me just scroll for a second. This started in September 7th, 2023, and this wasn't the first attempt, right? I had another attempt before this. This is literally a year and a half old, right? Scroll, 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 scroll. Scroll, scroll, bunch of segfaults. Scroll, scroll, scroll. Scroll, 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 scroll. Scroll. This has been just insane, this discussion. And the thing that was the most frustrating was the following. So just at the end of Christmas last year, I'd finished everything up. Everything was working. We had decent enough benchmarks that showed that like we're the same performance as master. Everything's great. There were three small things to do. One, we had to figure out some precision issue that was basically making the tests to fail. Turns out, there's nothing we could do about that. That's just something that was broken elsewhere that could be fixed later. We had to double check the AMD tests and check precision there as well. I did, it's fine. And then last, all we did do is change the documentation so that all of the GPU equals true in the documentation were changed to modify, to reflect this particular PR. That is to say, it now says we're reading in an array type instead of just setting GPU to be true. That was one of the main things that we did here, which was to allow people to dispatch on different array types. That's what we did. Now, then something happened, and after this was all done, again, a year and a half of effort from my part, like just kind of going back and forth, getting this to work. It's been an intense, long time of me getting this to work. For some reason, they decided they would merge in an incredibly large change to the underlying GPU kernels. And I was like, but why couldn't you have just waited? Why couldn't you have just waited a week? Why couldn't you have just reviewed my code, gotten that in, because I've been waiting for a year and a half to do this, and then put the CUDA code where it belongs instead of having to do it the other way around, which is way more annoying, right? And so I had to do the same thing I'd done 4 to 5 times before, which is to rebuild everything from scratch, because unfortunately he changed the one code, the one file that I've completely deleted and had to repurpose into different areas, because he changed CUDA.jl, which now no longer exists because we're not directly focusing on CUDA anymore. We're focusing on generic kernel support, and the CUDA.jl stuff needs to go into a separate extension specifically for CUDA users. So it was just one of those things where like I hate to say it, but this really did make me very angry. Like not like very, very angry, but I was like, man, I was in the middle of dealing with some drama, dealing with the Jack stuff that I mentioned the other day, and dealing with some paper that I was writing where there was like some weird, like not quite fraud situation happening, but like somebody was definitely kind of borderline doing things that I do not believe are okay in terms of academic integrity. And so I was angry at like a whole bunch of different things. And then while I'm working on this, this person sends me a message, oh, by the way, I've completely changed the code, therefore you cannot merge it. I'm like, guys, it's not, again, I'm not upset at Joe, who's the main developer here. Look, they're doing what they have to do. I get that. I'm not upset at like Jack people. Look, they have to publish or they perish. I get that. I'm not necessarily upset even at this person who was like messing up the paper that we were writing. I think they just did not know any better, right? But just when you add all these kind of annoyances together, I was very pissed off last week. Oh, and my kid's still not sleeping through the night. So I was like, geez, I cannot do this anymore. I was so mad all last week while I was working on this, By the way, Kiswick, hey, how are you? By the way, how do I pronounce that? Keswick? Need to listen for a while to say something intelligent. Yeah, that's fair. I don't know. I will say there was a conclusion to a discussion that I had the other day. So I'm not fuzzy. Keswick. I see. Thank you. Keswick. I'll remember that. So there was a discussion I had the other day related to some political. Again, I do not want to talk about politics too much more, but what I do want to say is the following. There was a very long discussion thread in the video that came after the live stream about, Trump's executive orders and all this kind of stuff. And a lot of people were just claiming I'm very much anti-Trump. And look, I don't like the guy. I think he's an idiot, and I am definitely anti-Trump. But I don't think anything I said was unfounded. I think everything I said was pretty clearly, at least at least you could understand where I was coming from, even if you do not agree necessarily with my conclusions. And if you didn't agree, I was more than willing to listen for people who give me like academic papers or something like that. But there was one guy in the comment section who was just not having it. He was so frustrated. He basically said that like everything that I was doing was just a like, basically was unwilling to listen to anything I had to say, and that's okay. But I will say that there was a conclusion to this discussion, and I think even if people hated that video and think that I really should not have said anything about politics at all, I do understand that perspective. But I think it was worthwhile, if only for this one conversation I had with this one person, where even though we don't necessarily agree with each other's stances, I feel like we were able to see each other, like look at each other in the eye and say, hey, look, this is what we believe, and it's okay that the other person believes differently, and maybe able to open up, open up the discussion to this type of stuff. I think that's the type of conversation that I think I would like to have about politics moving forward. Like, if somebody has an opinion that is radically different than mine, I would like to at least engage and understand where they're coming from, and to let that be the default. I don't necessarily have to convince them I'm right. I think by the nature of having a discussion, we will figure out like what we believe, and it will help us create a more like definitive stance on our own beliefs, and I think that's fine. But I just want to say that I'm very happy I did that political conversation, even if it means that I lost some subscribers or people were unhappy with it or this kind of stuff. I know I made a couple people upset, but I think it was worth doing. Hanif, Nihat, hey, thanks so much for coming in. So, let's get this done. So right now I'm running into an error. Let me move this over there and here. So the error is specifically this one. Okay. Evaluate is approx. Wait, is this actually correct? This is a failed test. This is not the one I was looking for. I think this is actually... What is this? What is this failure? This is not the one I thought it was. Oh, no, now we have more. Oh, no, this is it. Number matching length of nothing. So what happened was... Okay, here's what happened. So in one of the big changes that were pushed recently, there's this concept known as a neighbor list. Now, a neighbor list is essentially the connectivity path of all of these particles in an MD simulation. So if, for example, these particles here are too far away from this particle here, let me draw this in a different color. So if, for example, these particles here are too far away from this particle here, we might just consider the particles that are in the neighborhood of this guy, right? So by that I mean, we only consider these guys, and we do not consider these that are outside. And in doing this, we create something called a neighbor list, which I'm going to short down to NL, neighbor list, but I think the code actually says NBS for neighbors. This neighbor list allows us to cut down on computation because, you know, it is still an n-squared operation, but now the n-squared operation scales based on the number of neighbors for each person. So there's like a factor on top of this, like 0.5 or something like that. Oh, there's, you know what I mean? Like we cut down the number of computational units that we need to do, which is good. You know, because again, this does not scale very well. We have to find everything we can to fix that scaling issue. Now, one of the big changes that was recently done, and one of the big differences between the code that I was working with before and the code I am currently working with now, is that the way in which neighbor lists are computed changed. And in one of those ways, it basically made it so that the neighbor list calculation, which used to be basically like a nothing element, like if there was no neighbor list, basically I need to find a way to make it so that for the energy calculation specifically, not the force calculation, the energy calculation, we have a kernel that acts for the case where there is no neighbor list available. That's what we have to do. That's it. Is there some sense the ignored stuff is sort of symmetric besides being far away? So there is some symmetry here. Like obviously if we have two particles, A and B, interacting with each other, the force is equal and opposite, right? And so you can you only calculate once and you can get rid of the other calculation. So you can already cut by a factor of 2 just by dealing with symmetry. But the unfortunate case is that these particles are randomly distributed. And so like some particles might have a neighbor list that is like, I don't know, 10, 20 particles in size, and another one might have a neighbor list that's like 100 particles in size. You know what I mean? It just depends on how many particles are in close proximity to the other particles in the fluid or the whatever you're simulating, right? It could be like a plasma, it could be whatever. You know what I mean? Like, so whatever is in the fluid, it depends on the localization here, which is actually why neighbor lists are kind of annoying to do on the GPU, because on the CPU, you do like a list of lists type of situation. But because it doesn't necessarily have a static size, it means that when you do this on the GPU, you've got to be very careful about like accidentally allocating too much data or this kind of stuff. You just have to be careful because you don't want to like allocate unnecessarily. You know what I mean? These allocations are expensive, right? They're expensive on the CPU too, but not as expensive as they are on the GPU. And so neighbor lists are not necessarily easy to implement on the GPU, which is probably why it's a good idea that they did refresh the neighbor list computation for Molly. That's great. I'm really happy they did that. But it's one of those things where I wish they would have finished it, after my code had gone through, just because it's been quite frustrating to consistently write and rewrite this thing. And at the end, I don't even know if the person's going to merge it, right? Like, I've spent a long time on this, like unnecessarily long amount of time on this. And again, it's for code that no one in my project is actually using. It's a mess. It's a mess, but that's okay. I'm ranting. That's what happens. All right, so let's get going. I want to go ahead and pinpoint this error, and I want to get rid of it. So we're going to go over here. We're CD into projects, CESMIX, Molly. And let's get done. So right now, the issue is in, where is it? It's in basic.jl1. That's not true. It's in, where is this? No method matching length of nothing. And in particular, it is basic length 182. Let's go take a look at that. So let's go to vi test basic.jl, and let's go to 182. And this is going to call isapprox array of mean of sys coordinates atol. So the mean of sys.coordinates, that's what's failing, I believe. So if we go to mean, where is that defined as? Isapprox, no method matching. So pairwise PE GPU kernel, that looks like that's where it's failing. So we go to kernels.jl line 233. vi source kernels, and we go to line 233. I will say the following also, like, the stuff that I've been doing with Quibble, which is a animation or rendering engine that I've been working on in OpenCL, I'm like kind of a fan of C error messages. Like, I remember back in the day that I was not particularly happy with C++ error messages, but I wasn't particularly upset about them. I found them easily readable. Julia error messages, look, as much as I know this is a petty thing. I know it's petty. But like, man, Julia error messages are next level difficult to read. I'm so sorry, but it's like next to impossible. You know what I mean? I can't even explain why they're so hard to to read. Like, here it says spatial test failed. So we had a failed test. Cool. Okay. Stack trace. Macro expansion of this guy. So there was a failure at test.jl, but I don't care about test.jl. I didn't write that code. I can't fix that. Basic.jl I can fix, but obviously I'm worried about why the test failed. And not so much about like that it failed, you know what I mean? So this is just pointing to the test. What I want then is this stack trace down here, which indicates that there's an error during test, right? So here's a test failed, and here's an error during test, and that's what I was looking for. It's quite, I don't know, it's very difficult to read. And then look at the error message, right? Look at this. The stack trace is so long, and the only thing I needed was this line down here, right? Why is the stack trace so long? I don't know. It could be because the type system is like incredibly big, and they're being overly pedantic. I don't know. And when we're talking about kernel abstractions work, it's another level difficult to read. It's like, it is probably the same issue with C++ that you're talking about down there with Hanif, where like basically because it's metaprogrammed and then metaprogrammed again and then turned into LLVM and then spit out into the LLVM-like language, the compilation process is just so complicated that the error messages here are very difficult to get right. I understand that. I get that. That's not a big deal. It's just that, like, again, this is a very petty thing that makes it very difficult to write code in Julia sometimes. Surely it can't be worse than LaTeX errors. To be fair, LaTeX errors are definitely worse. Like 100% definitely worse. Time to rewrite in Rust. Look, here's the thing about Rust. If the Rust GPU ecosystem actually turns out to be good, I'm more than willing to try it. But right now, Rust is so far behind on the GPU game that it's very difficult for me to recommend it for people who actually have to do GPU computing. That is not to say it won't catch up. I think it can catch up. But Julia has almost 10 years of integrating GPUs into the language, right? In such a way that it is just by a mile better than, like, I don't necessarily recommend CUDA, but I can recommend Julia GPU because it is so much better than pretty much any other GPU ecosystem out there. If you're doing GPU computing, I don't think Rust is the best choice right now. Now, that said, everyone knows that GPUs are the future, and because GPUs are the future and present, to be honest, I think there are a lot of people who are focusing on GPU computing in Rust, and I think that could lead to really good development of this toolkit. But I also wonder, because Rust has its own very specific niche for like certain systems, I do wonder if that's actually even a priority of the community or not. It is a priority of the Julia community, but it might not be a priority of Rust. You know what I mean? Rust error messages aren't always the easiest to read either. I think the core features that makes Rust stand out are useful for GPU computing. I don't think the core features that make Rust stand out are useful for GPU computing either. I think I agree with this statement as well. But to be fair, the core things that make Julia good are not the same for the Julia GPU ecosystem. Like, GPUs are different, right? And I always make this claim. Like, I always say that Julia is different than Julia GPU, right? And if you care about GPUs, Julia GPU is great. But sometimes Julia gets in your way. Right, that's what I say, right? A lot of the things that people care about in Julia, like flexibility, composability, all this kind of stuff, whatever you want to say, like, a lot of that stuff is just not viable on the GPU. Like, there's a lot of like metaprogramming you just can't do on the GPU. And if you're used to GPU programming, okay, yeah, for sure, everybody knows this. But if you're not used to it and you're coming from Julia, GPU computing is still jarring. It's always going to be jarring. But in my mind, like, it's not the GPU computing sector that's weird. It's the Julia sector that's weird. It's like things like broadcasting. It naturally works in parallel on the GPU, but it doesn't work in parallel on the CPU. You know what I mean? Like, there's like weird things about it. And for the people who don't know what broadcasting is, here, let me just give you an example. Julia using AMD GPU. 1 second. I'm catching up on chat, by the way. A is equal to 1s. Let's do 10, 10. And then B is equal to rock array of A. So this is the GPU array. What I just did is I copied the data over to the GPU. And now if I do, I don't know, C is equal to AMD GPU dot zeros, I don't know, of like 10, 10, and we say A. Point is, I'm like creating a new array. Hello, it's taking its time, isn't it? And then we say something like C is going to be dot equal to B dot plus B. What I'm doing here is I'm creating a kernel that basically takes every element of B and adds it to another element of B, and I'm running that, right? So this allowed me to very quickly spin up a GPU kernel. If I were to do this with CPU arrays, just normal arrays, it would not be in parallel. But because this is spinning up a GPU kernel in the background, it's natively in parallel on the GPU. And there's a lot of just like weird jank dealing with the way in which Julia GPU integrates itself into Julia. And I would have loved if the creators of the Julia GPU ecosystem were instead to either be more forceful about the requirements of GPU computing for Julia, or if they were to have considered doing what they did in another language. You know what I mean? Like, maybe if they would have done it in Rust, it could have been a little bit less janky. But there's a lot of things that are really beneficial about Julia that, you know, like, it gives you good reasoning about the lower level representations and stuff like this. It's good. Let's see. That's insane. Even Java error print first the message, then stack trace. Right. It is a very weird error message. And like, to be clear, kernel abstractions makes it worse, but I don't think this is a situation where we actually are using kernel abstractions. Is it compile error or runtime error? So this is what is this? So I think there's two tests that have failed. One has failed and another has errored, right? So this one is actually like a precision error or a precision test where like the precision has not, like, we expected like 270 and we got 269.9. You know what I'm saying? Like, it's just not quite what we were expecting. Now, this then is an error. And so this one is because the way Julia works is it happens to do the compilation at the time in which the types are known for the function, right? So it's just barely ahead of time. So the compilation happens function by function, but only when all the types are statically known, right? And so what happened here was we had a type that was not necessarily statically known, and we tried to use that in a function, right? And so it tried to compile that, but it only compiled it while it was running. So it's kind of like a mix between a runtime error and a compile time error. It's compile time that happened during runtime that caused this to be an issue, I think. But it also could just be, I don't know, some type issue, because it clearly what's happening here is that we had a variable that was called NBS. It was a nothing. It is nothing. That is what it is. And you can't do length on a nothing. And so that's what it's specifically saying the problem is. Rust borrow model doesn't fit kernels easily. Like, writing, for examples, needs unsafe to split data into each thread. Yeah, this is also an issue we have with Julia, in that, like, people are very heavily relying on like garbage collection in a lot of different Julia programs, but garbage collection on the GPU just sucks. No, you don't use garbage collection on the GPU, guys. Like, you shouldn't. Now, people will say that, oh, because it's a garbage collected language, this makes it so it is, you know, no longer viable for a vast majority of calculations or of computation, of projects. I don't necessarily go that far. I think the garbage collector on the GPU is bad, but similar to what you have to do with any manually, manual memory managed language, like for example Rust or C. As long as you're careful about your allocations, it's fine. And it's going to be fine. Like the main thing is just be careful about what you're allocating and deallocating. And Julia helps you keep track of those allocations relatively easily, right? Do you have a regular schedule or at least an approximate time for your stream? The truth is right now, I don't necessarily have that. I'm streaming when I can. Once this MIT project finishes up and I can kind of close out some meetings in the afternoon, I will be able to stream more regularly at my time zone from like sometime vaguely in the afternoon, European time. Right, so this would be Spain time, right? And so right now it's 12:30 my time, and I am hopefully going to be able to stream sometime vaguely in the afternoons from the foreseeable future. But also, it's a question as to the type of content that I want to stream. And sorry, I have to cough 1 second. Oh my goodness. I'm so sorry. I'm still a little bit sick. But yes, it's a question of the type of content that I would like to stream. So for example, this stuff is like, it's 50-50 as to whether I should stream it or not, that type of stuff, Right. And so with that said, it's the reason I've been so scattered for streaming recently is just because I'm not always clear as to what the type of content I should be making is. But as that becomes more clear moving forward, I should be able to create a more clear schedule. For now, it's like vaguely in the afternoon European time when I have time. But I should be getting more time available like starting next month, and this should allow me to do more regular streams. Speaking of which, this is why I'm dual streaming on YouTube. It makes the VODs immediately available for people to watch if they want to. And so people who do want to just like hang out, listen in, I personally find myself watching VODs from streamers all the time. In fact, I would argue that's probably the main content I watch on YouTube nowadays is VODs from streamers I enjoy. So I think, like, I understand that audience, and this is why I want to make sure that I have, the YouTube stream going on at the same time and all that kind of stuff. This message seems about on this level of C++ template errors. I think you might be right. What distro are you using? I'm using Arch Linux. In particular, I'm using the OpenBox Windows Manager. You could argue I should be switching over to Wayland, and I would agree with you there. The only issue is that I have not found a compositor in Wayland that really makes me feel happy to use it. OpenBox, I love OpenBox. I'm such a big fan of OpenBox. I've been able to configure it to be exactly what I want. The only one I saw on the Wayland side was Hyperland, but there was something, I can't explain what happened, but there was something about the Hyperland community. I asked a question and it rubbed me the wrong way. And you could choose to use software for whatever reason you want. I don't exactly know what happened. Maybe there was just something really weird going on in the community that day. But when I went to the Hyperland, Discord, I was asking questions on how to use certain things. Because look, it's not necessarily straightforward. There's some, coming from other Windows managers, it's not very clear. Just there was something weird going on. I don't know what was going on. They were talking about issues that I was completely on the other side of politically. And it's like a Windows manager. It's like a compositor. Why does this matter? You know what I mean? Very weird stuff. I could not figure it out. And so I did actually appreciate my time using Hyperland. I don't know why I'm rambling about this, but I just somehow I was like, man, maybe I should just wait to do this whole Wayland thing until there's a compositor that I'm actually happy with using. The core issues are that I use a drawing tablet as a mouse, and it's very difficult to work with dual screen. Just the X Wacom package that I have right now to manipulate this drawing tablet so that I can use it for what I need, it just doesn't exist yet in Wayland. So to use this drawing tablet as a mouse, I have to have restrictions on how I usually use it, which is annoying. It's not a big deal. I have a mouse I could use. It's just, mice hurt my fingers. I'm sorry. I don't know why. I get carpal tunnel very easily. I can't explain why. Just if I click too much, it hurts. So I use this instead. It helps me with my hand situation. And then there's a few other things sharing screen is a little bit annoying. There's just a bunch of things that are just kind of annoying. I like X11. Wayland hype is too big. Yeah, the thing is, Wayland hype was big 10 years ago, and it's still big. People are this is the future. But if it's the future, why isn't it here yet? You know what I mean? Why are so many people focusing on this, and yet we haven't gotten any legitimate. I understand that GNOME and KDE are both using Wayland now, and that's fair. I haven't gotten there yet. Sorry, guys. Rust borrow model doesn't fit with kernel easily. Okay, so anyway, that was my Linux rant. I'm so sorry. Every time people bring what distro, when they ask me what distro are you using, it's really difficult for me to answer because I think what they're actually asking is what Windows manager are you using? Like, how does it look like this? Not like not specifically the distro. I don't think people care if you're using Arch or Ubuntu or Fedora. Like, this doesn't matter. You know what I mean? What does matter is your Windows manager and how you set up your system to look that way. I think it's even pinned on Discord. If you go to Discord, you can find the exact files that I used to create this. Anyway, I'm rambling. Let's go. Oh, also. There was one guy, like one commenter, who mentioned that some of the videos I put out recently are like incredibly off topic. I'm like, what? I mean, you're right. They are incredibly off topic, but they're definitely not off brand. Like these type of streams are like, this is the bread and butter of Leos Labs content, you know, like a random stream where we're rambling about stuff that's vaguely related to the topic at hand, and it ends up being 3 hours and we got nothing done. Like, that is the stereotypical Leos Labs stream. I would love to say we are getting work done every stream, and we usually do, but the amount of stuff that we get done is much less than it would have been if I would have just like sat down and worked outside a stream. And yet I convince myself every time that streaming is beneficial because, I don't know, it is beneficial. I really appreciate you guys being here, but like, it's like, am I actually working? Good question, and I don't think the answer is yes. All right, so let's go ahead and cd or clear here. And now let's go into VI source, kernels.jl, let's go to line 233. So specifically the issue is this call right here, length of NBS, where NBS is a nothing. Now we've already done this before, in that if we go to the pairwise, what's it called? A force kernel up here. Pairwise force kernel nonlinear. Sorry about that, man. I'm sick, and I'm trying to do my best to not sound sick, but I don't think I'm doing a good job. So, here's what we did before. For pairwise force GPU, we basically said if type of NBS is equal to no neighbor list, which basically means that we have a nothing there, then we go through this operation. If there is a neighbor list, then we do this operation. Now, I'm going to go ahead and copy this down to the pairwise potential energy, whatever that was. Pairwise PE, and essentially we want our function to look like this. So let's go down here, and let's go ahead and paste this down here. Okay, so backend is get backend of coordinates. That's fine, and we say if type of neighbor list is equal to no neighbor list, which I think if you do type of nothing, this is the thing that's a little bit weird. I'm not entirely sure if this is going to trigger, and the reason I don't know if this is going to trigger is because NBS is nothing, not no neighbor list. You know what I mean? And so I need to double check how this neighbor list is being called in the code in order to like send in a nothing versus a no neighbor list struct. Does that make sense? Like, we have a type that is no neighbor list, and we have another type that is nothing. And right now I think NBS is nothing, but it should be no neighbor list. You know what I'm saying? Okay, maybe you don't, but that's okay. I don't know what I'm saying either. So, but in principle, the code should look something like this. So when we do GPU threads pairwise, that's fine. Pairwise potential energy kernel, no, I think it's this one, PE kernel. And then we do the kernel and we call it with the appropriate function argument. So we do the same thing here. We do pairwise PE kernel. And so in principle, that's what we're looking for. And we want to return PE vec no units. PE vec no units. And I think all I need to do now is I need to make sure the kernel is called with the appropriate arguments, which will be, let's see. Is that actually correct? The one that we have down here? I believe it is correct. So let's go ahead and just do $, DD there. I'm going to do J and then $, again. Oh, U. I want to do actually D, that guy. No, that wasn't right. Okay, whatever. I'm just going to, what, D? That, right? Yeah, that's what I want. There we go. And I'm going to do the same thing up here. So we're going to do $, DD, it doesn't matter. Okay, now we just have to get the right arguments in here. So similar to the null error. I guess it's something like that. It's just, essentially there's a type mismatch here that I have to figure out. That's it. And then I also have to make sure that we have the pairwise PE kernel no neighbor list also implemented, because right now we only have the pairwise PE kernel, but we need one for no neighbor list, which I think should be relatively straightforward. I just haven't done it yet, so I just have to do it. It's not hard, I just have to do it. All right, so let's first put in the appropriate arguments, which should be these arguments in here, I hope. There we go. Comma. There we go. Should be fine. Now, this is not going to work because the length of neighbor list is not a value that we can use because this is for no neighbor lists. And again, neighbor lists are like the list of neighbors that each particle will be interacting with. That's what it is. So in this case, then, if we don't have a neighbor list, my guess is that we're going to have to do length of sys.chords, which is going to be the total number of particles we have. Let's go down here and let's do the same thing. So we're going to have to put in these arguments. Pevac, no. I'm doing great. How are you? By the way, I feel like it's been a while, Zabata, since I've seen you. How you doing? Maybe I'm wrong. Maybe I've just completely forgotten, and you were here like last stream, and I'm just, you know, dumb. But yeah, how are you guys doing? How are you doing? And how is everyone doing? Okay, so backend, nthreads, GPU. I think everything else is the same, so we can just go ahead and delete this block. And then we've got to re-implement function pairwise PE kernel, but this time for no neighbor list. So what I'm going to do is I'm going to go up here, and I'm going to delete a couple lines there. And then I think what I want to do, there is another option where we don't have a separate kernel, and instead no, we're going to have to implement a separate function. That's the only way to do it. Okay, let's go in here and let's implement another function. So let's see how many lines do we have here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 20, 22, it sounds like. All right, yank 22 yank. Oh, DD yank 22 yank, and let's just paste that bad boy up there. And now we're gonna say pairwise PE kernel, no neighbor list. Yes, it's been a really long time. I hope everything's okay. Yeah, it's okay. It's okay. Generics. Wait. So it might be possible to make this more generic. And this is what I was thinking about. On the other hand, this splitting between the neighborless kernel and the no neighborless kernel is what has already been, like, is what people have already done in the code at this point. And so I don't want to, like, rock the boat too much. We already have this distinction between neighborless and no neighborless. So let's just keep it for the potential energy as well, because we're already using it for forces. I don't want to rock the boat. I want this code to get through. And that means minimal changes to the rest of the code. And instead maybe arguing that, oh, it'd be nice if we did this in the future. But, like, again, each PR should be its own distinct thing. And this PR is already, I mean, let me just go ahead and check. I think it's like, let's do pull requests. Let's go to kernel abstraction support. It is already 2,500 lines changed. And so I don't want to rock the boat more than this. I'm already rocking it. I don't want to rock it more. You know what I mean? Like it's been a lot of work for this particular project to get this done. So sorry. All right. So let's get this done. So no neighbor list. I'm just going to go ahead and I think, what do I want to do even? What am I doing with my life? That's always my question, and I never really have an answer. Maybe one day I will, but today I don't think I do. So let's go here. Do that. Sometimes I feel like all I'm doing in life is adding white space to Julia code. And like, it doesn't even matter. It's not like Python where white space matters. You know what I mean? Like, who cares? Anyway, let's keep going. Index global linear, that's fine. If about how many active Julia contributors are there? Could you qualify the question? Do you mean Julia contributors like contributors to the Julia language? Or do you mean like people just writing Julia code? For the Molly project right now, I think there's like, I mean, we can check, right? Insights, contributors. I think it's like, let's see, how many contributors are there? Oh, look, there's a good number, right? I don't know how many that is, but it's a good number. Let's see, so that is 8. That is 16. That is 24. So something on the order of 27, 28, maybe 30. That's pretty good for a thing of this size. I think that's fine. Yeah. Contributing to the language. To the language is probably quite large. Julia Lang, GitHub. I mean, it is very large. So let's go. I mean, I can't do insights, can I? I mean, I guess I can try. Oh, wow. Valentine is number 2 for this past month. That's actually quite impressive in a way. Contributors. I don't think this is going to give me any data that's actually worthwhile. I mean, look, this is such a huge project. I mean, how many lines of code do we even have in Julia? It's going to be like, does it give me the lines of code? Period all. Oh yeah, they recently changed this to make it so it's like hard for me to see, like, I don't want just contributions. I want like lines of code changed and stuff like that. My open source project is very large and doesn't have a ton of, it doesn't have a ton of contributors. That could also be true, but I think Julia in particular does have a large number of contributors. It's one of these relatively easy languages to contribute to. I mean, like, we're scrolling for a while. By the way, Nick, hey, how are you doing? Okay, it's being actively developed. Yeah, look, it is definitely being actively developed, if that's what your question was. 100%. There's a lot of changes happening right now. So, I mean, just there's 1,000 pull requests open right now and 4,000 issues, and people are actively working on it. How does one get in your line of job? I'm working in CUDA and game dev, but I feel like I would like researching. That's a very good question, and I'm not entirely sure what you mean. So, if you're working at CUDA and game dev, these to me are two distinct, like, things. You know what I mean? Like, CUDA is usually for like computational simulation, whereas game dev is usually like more like computer graphics. And though they both use the GPU, it's usually rare that you see so much overlap between CUDA and like game development. It happens all the time. But the situations that I see it come in are like software rendering methods and stuff like that. It's more like enhancements to game engines and things like this, rather than like game developers actively using CUDA. So I think it's quite interesting that you're already at this intersection between CUDA and game dev. And there's actually a lot of really cool things that people are doing right now in the research area that I would consider looking into. So if you are very interested in doing like these software rendering approaches, one really cool thing that people are looking into right now is like Gaussian splatting models. So if you look up Gaussian splatting, you learn about it, and you implement like rendering engines with this in mind and stuff, like you could very well get some papers out in SIGGRAPH and stuff like that. SIGGRAPH is like the leading conference for computer graphics. Is one that I'm shooting for in the next year as well, with actually my own research project that is related to this type of stuff. In fact, I would extend an open invitation to anybody watching this as I start moving towards research later on this year, like once the GPU book is done and I start moving towards the computer graphics engine type of stuff that I've been doing for research. I'm obviously encouraging anybody watching and who wants to contribute, you know? And so if you are interested in getting your foot in the door for research, I'm going to try my best to make it so that there are like things that people can do to start contributing to research, even if they are outside of academia. In Europe for the week. Oh, happy to hear that. I'm also in Europe for the week. Unfortunately, I'm always in Europe. Or maybe more fortunately, I'm always in Europe. But yeah, I hope you enjoy your time. Or I don't know if you're on vacation or if you're there for a conference or whatever, but I hope you're enjoying your time. Particle systems use compute shaders. That's true. Particle systems do use compute shaders. And there's like some other things as well. Like ray tracing for the longest time was better on software than on hardware. That is to say, used to be that people would always implement their own ray tracing methods or path tracing methods to be used in video games via software rendering. So that's another thing that people use a lot. A lot of the signed distance field stuff that you see a lot in Shader Toy, I mean, this is not active research, but there are very interesting applications here that you could use going forward. I always care about like language design and like composability and stuff like this. And so it's, oh, you work in Malta. It's very pretty. Yeah. I hope, yeah, this sounds great. Even if it's only for a week, that sounds great, you know? Yeah, I don't know. Some places in Europe are just pretty. I don't know how to put it. Like somehow in the US, I feel like every city is kind of the same. I mean, I was in Boston, I was in Alabama, I was in, California. They all feel the same, but like, in Barcelona, where I'm at right now, like, man, you go down the street and it feels completely different. You know what I mean? It could just be because you've got hundreds of years of development of each city, which leads to like different eras being like present in the architecture throughout different places. You know what I mean? But it's cool. Oh, Inigo Quiles has so much material in SDS. Yes, exactly. That's someone I would definitely recommend for SDS. Really cool stuff. If you guys don't know Inigo Quiles. Sorry, when you said IQ, it took me a second to realize who you meant. Yeah, like this is. Look, it's amazing. Like, look at it. Oh, not. This is not him. Don't. This is an advertisement, just for the record. I hate advertisements. They're the worst. But yeah, so this was completely made with signed distance fields, which is basically a mathematical representation of objects. The rendering engine that I'm building should be able to do very similar things, but it's kind of in its infancy. So it's going to take basically a full year to get to the point where I'm happy with the results from the stuff that I'm doing later. But for now, I need to finish this MD stuff. That's what I have to do. I have to finish up the MIT stuff before moving on to actual research projects, I will say the following. For people who are very interested in research, there is a tendency for researchers to follow a very stereotypical academic path. That is to say, you go through a PhD, you then go through a postdoc, you go through whatever you need to get to professorship, and then as a professor, you then teach students and you apply for more grants and start building your own research team and all this kind of stuff. So research tends to be very academically minded, academically focused, but that doesn't necessarily mean that's the only way to do research. You can also do research in industry. There's a lot of good companies, like for example, Google, IBM, Pixar. These are companies that are doing research, active research, in order to put products out, right? And so if you're interested in doing that, it could be a matter of just finding the right people in the right industry that you want to work with, and then slowly but surely working your way into that area. You know, I missed 1 hour of exactly the topic I want to dive into. Ask the question again. I can repeat myself. Also, like if it is something we literally just talked about, I'm more than willing to. Again, I can repeat myself, or you can go to the YouTube video where there's a VOD and you can go back and stuff like that. Yeah. The stream title. What is the stream title? The stream title is MD and GPUs. Wait, stream title on... Are you talking about stream title on YouTube or stream title on Twitch? The stream title on YouTube is like my most recent failure. You know what I mean? Stream title on Twitch is like MD and GPUs. Somehow I just felt like my biggest failure was like clickbaity. You know what I mean? I don't know. YouTube, I feel like I have to be just slightly clickbaity. Like, not super clickbaity, but like just enough that it's like, you're watching, you might click on this, you know what I mean? Whereas for Twitch, I feel like I want to be very clear as to what I'm doing, because there are other people, like I need to differentiate myself from like the number of other computer graphics or computer science streamers, you know what I mean? Whereas on YouTube, I have to differentiate myself from like Mr. Beast, you know what I mean? So it's like a different level of clickbait. Like it's like when I go to the archive, those papers will clickbait me, but they obviously do not clickbait the average, like Logan Paul viewer. You know what I'm saying? Like you put different clickbait for different audiences, and I feel like the Twitch audience, I don't know why, I feel like they're slightly more technical, and like if you see a video or a stream from mine in the YouTube sub box, let's say, it's for me. If you know who I am, you're probably going to click it, right? You don't need to be clickbaited. If you're already a sub to me, you don't need to be clickbaited. It's for people who are outside of the community, and that's, I don't know. I don't think clickbait's necessarily bad, but I do recognize that maybe I should be a little bit more consistent with what I'm saying on both platforms. Then again, I'm streaming to both platforms at the same time. What am I saying? What am I talking about? I don't know anything. Okay. So yeah, in terms of like GPUs and all that kind of stuff, literally all we were talking about was the path to development for this project so far. We talked about how my project was basically to do GPU MD simulations. I had multiple different solutions, this one, and then like I kept working on Molly again and again. I had to update the Julia GPU ecosystem in order to get this done. We talked about how the neighbor list works, why we have individual particles. So basically in a GPU simulation, you have each individual particle dealing with all the other particles in the simulation. So you have n particles doing n operations on the other particles, right? So it's an n squared operation. You can cut this down by adding a neighbor list in and using some symmetry arguments, but for the most part, it still scales as n squared. So it's not the best for GPUs, but you can still get a big speed up. And that's basically all we said. I'm now just writing the code and getting it done. I need to get this done as soon as possible, but like after the development journey that this particular project has been on, I am notably a little bit tired of working on it, and so I need to like motivate myself via external means, and that's also why I'm streaming, you know? Okay. At inbounds, if inter I is less than the length of neighbors. What is inter I? Inter I is the inter index. Cool. Length of neighbors. So we don't have neighbors here. So I think what I have to do is, why would I ever need this? But it's okay, whatever, I don't care. There's no situation where this is useful, but I will put it in there. Length of chords. It's fine. There's no situation where I will need this because the indexing is already done by kernel abstractions, but I'll leave it in there. Or maybe I don't. Screw it. I don't care. I'm taking it out. You guys are going to just deal with it. I don't care. I'm going to be a rebel today. Wow. Okay. So ij special is equal neighbors of inter j. So this is one issue in that we don't have neighbors in this case. So I have to figure out what ij and special are. In particular, I don't know what special is. So again, we don't have neighbors. So I need to remove neighbors from this guy up here for the no neighbor list. And I have to figure out what special means. Like what does special mean? Like what does it mean to be special? You know? I don't know. I don't think anybody knows. So let's go ahead and remove this. Okay, so I, j, and special. So what is I and what is j? In this case, I'm going to do for I is equal to 1 to length of chords. I guess probably what I want to do is not length of coordinates because we can deal with the symmetric argument here. We probably want to do length of coordinates, and then we want to do minus inter I. I think is what I want. Let me think about that again. But essentially what we want to do is have every particle interact with all the other particles. They're represented in this giant matrix. And so particle 1 interacts with all other particles, right? Except for itself. Okay, so yes, that's what I want. So it should actually start at inter I, and it should go to length of coordinates. And I think I want inter I plus 1, so it avoids itself. I think that's what I want. Good. And so now let's add the spacing back in down here. And let's go here. Okay, for I is equal to this. And I think I actually want this to be called J. Because I think that's what we did before. J. And I think I, in this case, is just going to be this. So now we can do this. Enter I. There. So if it isn't n squared, then the axis of particles means not so nice memory accesses. Or, yeah, so the reason the n squared matters is because it's a computational complexity scaling, not necessarily a memory access scaling, although you do need to access the memory every time. So like you have this, you basically have an array of particles in global memory, right? And it means that every single time you have to do a simulation, you're gonna have to take a single particle, one array axis, and then you're going to have to access every other particle in the array. So that means you're gonna have another, basically it's n squared memory accesses as well. You're right. But there are ways to trick this by putting it in shared memory and stuff like that. But that's essentially what you're doing. You have an n squared number of memory accesses, which will slow down your computation. And so you want to avoid that. This is also why you want to make sure that you're using like coalesced data, like the data is right next to each other and stuff like that. But for an iterative approach like this, it just means n squared in memory accesses. There's no way to really fix this. But it's just a bad thing to do on the GPU. So we already have I, we already have J. Now I have to figure out what special means. What is special? Okay, so let's just go down here and just say special. Is that meant to be spatial? No, it's special. Equals, I don't know what it is, so I'm going to figure that out. So where do we use spatial? Special. It's used down here for potential energy GPU. Great. So we have to figure out where potential energy GPU is and what that means to be special in that context. That's okay. And I believe coordinates I, coordinates J, velocity I, velocity J, that should all be the same. dr should be the same. Potential energy GPU should be the same. We just have to figure out what special is. For inter is equal to inter 2 to end. Okay, I see what's happening here. I don't need this one. I don't need this one, I think. Oh, we do potential energies plus equal to that, right? And then, but down here we just do the energy plus equals U strip. So it doesn't look like we're doing, what is going on here? We're adding it all to the energy ones. This is summation. Weird. Let's see. Great work so far with the GPU kernel handbook. I like your writing style. Looking forward to reading updates as they become available. Oh yeah. Hey, were you the one? I think you were the one. There was somebody who was trying to access the Google form that I had written on yesterday's stream. It's not publicly available yet. It will be publicly available later. I just wanted to let you know that it's not yet there yet. I want to put that in with chapter 2. So like next week, it should be available. In terms of the GPU book, I actually modified it a bit and I shortened up some bits. So I'll just go ahead and show what I shortened up. So let's go into CD projects, books, GPU handbook, VI source, and then we go into content intro. What I did is I actually took 2 paragraphs. Okay, maybe I shouldn't. Okay, who cares? I can. These sections are together. So I took the big green elephant in the room and I combined them together so that it's like not as rambly. You know what I mean? Because it was like 2 long sections talking about how CUDA is great, but also we can't use it for this work. It was too much. It was too much. So I just reworked it all together so that it's less rambly. It means it's kind of less interesting to read, but also I think a textbook should be, it should be fun to read, but it also, the primary purpose is to present information, which is, I think, what this does. So I will say it has been reworked, and I think it has been reworked for the better. It doesn't mean there's still more work to be done. There is definitely still more work to be done, but I'm happy with it. The handbook right now as it is I'll show it to you, laoslabs.com/GPU-handbook. Is that going to work? Did I misspell my own? No, wait. laoslabs.com, GPU handbook, whatever. Here it is. This is what I've got so far. Is obviously just the introduction. I saw that as I went through the commits. Yeah, I was wondering where you found it. I was like, how did you find the forum? Anyway, but that could mean that the actual forum is like giving the wrong link. So I need to check that as well. Let's go ahead and check that right now. So VI source index.md. But that could mean that this particular link is bad. This one. I think it's fine, but let me check in a browser and see if there's actually an issue with it. So I will go to I need something I'm not signed in on. So let's do Chromium. There we go. Let's open up this link. And access denied. So I need to make sure that this is publicly available for people. So let me do that right now. Okay, so Google Forms. But that did catch an issue, so I do appreciate that. So let's go here to sign in, I guess. Let's go to GPU Handbook Survey. And let's do, how do I make it so everyone accepting responses, specific people, do I just give people this link? Is that what I need? Shorten URL. Let's try this one. So let's do Chromium again. And let's go here, paste that link. And this one should be, no, it's still access denied. Why? Why is it denied? Do I need to do prefill form? No, that's not what I need. Why is it access denied? It should be accepting responses, right? So it's published. Accepting responses, yes. Responders, specific people. Maybe I need to do, this should be, responders can be anybody. People with access, general access, editor view, restricted, responder view, anyone with a link. Done. Save. Do I have to do that with my other forms as well? Let's go here, refresh, sign in. One second, I'm doing some stuff. I realize this is not related to, do I have to do this for everything? Oh, is this one not even sent yet? Link. Isn't this a bit weird? What was wrong with this form that I had to, Anyway, let me see if this works now. So let me give, check out this link, shorten URL, grab that link. Let's open up Chromium again. And let's paste this bad boy there. Okay, it now seems to work. And I will go ahead and post this link in chat. Where was it? Here's the form. So let's just double check that this works again. There we go. Paste that there. Good. Okay, so this is the survey in case people did want to go ahead. They can. Just for the record, and I just need to make this abundantly clear, I'm not expecting people to purchase this book. Rather, I would appreciate it if you do. But this book is going to be written over the next few months and is going to be related to just what I know about GPU computing using Julia as a way to express that information to people, right? Because I think kernel abstractions right now is actually genuinely the best tool that we have to do GPU computing and to teach GPU computing. But it's one of those situations where I have a lot of knowledge and I need to get that knowledge out. And so I think this is helpful for a lot of people. I appreciate it if you were to consider purchasing the book, but it's not necessary. It's going to be freely available for anyone to read online. That's fine. And so it's a situation where it helps me out because I don't put ads on the stream and I don't like ask for money or anything like that. And so like basically my business model moving forward is to push as many of these books out as fast as possible. Not as fast as possible, but to push books out that people can buy and have like a tangible item that they can like, you know, I don't know, like have in their hands, you know what I mean? Like, I feel like that's one of the most honorable ways to make money on the internet, like not via advertisement, but via like giving people actual things that they want, and that they are willing to spend money on. And so like moving forward, once the book is out, my intention is to basically use it as like a marketing tool, you know what I mean? Like just to say like, if you like the content, please buy this book. And I have other works like that as well that are coming in the future that are supposed to be just like things for people to buy, so that I don't have to put advertisements on my stream and I can do other things. That's the plan. So let's see. Is it not hard reading with the same color? So this is actually consistently every stream someone mentions this, and it is true. It is maybe a little bit hard for other people, but for me, like I find colors so distracting that I have trouble reading with the colors. You know what I mean? And so like it's just what you're used to, and I'm so unused to having color like highlighting, syntax highlighting on my code at this point that if I see it, it's like what is going on? Like why is this a different shade of brown or something? It depends on what you're used to, and I recognize that not everybody likes the no color. That's fine. Let's see. The handbook is already out there. Sorry to ask right now, what was the conference you mentioned about GPUs? It's SIGGRAPH. Here, I'll go ahead and give you a link. SIGGRAPH. So this is actually one of my favorite conferences, right? Not just because, so I have this thing about computer graphics. Okay, let me talk about computer graphics for just a second. So I am a researcher. I'm a researcher. I think that most people know that. I work at MIT. I have consistently worked at MIT for the past 5 years. Before that, I did a PhD at OIS. During this entire time, I was doing GPU computing, right? And I found myself to very highly appreciate computer graphics, right? And the reason I have like such a high appreciation of computer graphics is because essentially every computational algorithm that is used in computational physics, computational chemistry, or something like that that runs on the GPU in parallel has its analog to a lot of computer graphics algorithms that were invented a long time ago for graphical applications, right? You could argue that people doing computer graphics research were kind of doing the same thing as people doing computational science, right? Computational science focused on like a large number of distributed CPU cores, CPU computers, right? And they had to deal with that parallelism in order to get performance. Well, GPUs are the same thing. It's a massively parallel device used to do specific computation, and that computation rhymes between the two of them. It's not identical, but it rhymes, right? They're very similar between the two of them. And so when I see people doing computer graphics research, and I see people doing like fluid sims or something like that with computer graphics, I recognize the fluid sim doesn't have to be physically accurate. It's more or less a toy model to test what could eventually become physically accurate in the future. It's really cool. And so when I was doing my PhD at OIST, there were sometimes people who would like talk to me and they would say things like, they would say that like computer graphics research is not important because it's not like physics or chemistry or whatever. They'd say like computer science as a field is bunk. Like just a lot of these like weird things that I just could not disagree more. I think, to be honest, computer graphics is like the most pure form of computational, how do I put this? Fundamental computational research that you can have. It's a series of toy models with very clear applications and very clear goals in mind that allow you to test algorithms that you could not ordinarily test and see if it fits on the architecture. That has direct monetary impact that can actually modify the architecture so that you can do like more computation in the future. You know what I mean? Like it's like a series of these very interesting, purely theoretical like concepts. You know what I mean? That create stunning results. It's like, what's not to love? You know. Big fan of computer graphics. On that, don't try to roll your own engine, even rendering engine, it gets very large. I agree with this. So I have already written my own engine in Julia. It already works, and it's fast. It can get up to 5,000 frames per second. The issue is compilation time, which is why I'm rewriting it in C and OpenCL right now. It can get up to 5,000 frames per second, but unfortunately the compilation time in Julia can sometimes take minutes for each frame. In C, OpenCL, it can be like on the order of 100 milliseconds, which is good enough for what I want because you can just do a lot of the computation in the compilation in bulk at the start of each like scene or something like that. In particular, like what I want to do is to have like I have some very clear goals of what the animation is that I want to make, because what I'm doing here is not mesh based. It's not it's like fundamentally different than what people are doing on GPUs right now. And so the only way forward is to create my own rendering engine. I can't rely on pre-existing tools. Even like OpenGL and Vulkan are not well suited for this. I have to use a compute shader model or else kernels to do what I want to do. It's essentially a variation on Gaussian splatting, which obviously needs its own software rendering approach to be done nowadays. Well, maybe not obviously, but most people do it this way. And so I know it's kind of a daunting task, but I've already done all the work for it, and that's where I've been for the past 2 years. Like, if I was not streaming, I was probably working on this engine, and it's done. It's just a matter of like repurposing the stuff that I've already written into C and just kind of doing the animation now. So I know you're saying don't try to roll your own engine, but also like I already did it, so I might as well write a paper on it, you know? Gamers buy games and support science. Well, there you go. Yeah, sorry, you should have told me that 2 years ago, you know what I mean? Good stuff, your videos. Hey, I appreciate you being here, and I appreciate you saying that. In my opinion, I'd like to see if the contrast between keyword, variable, constant, function, etc., why naming convention for variables versus function constants are different. Computer graphics is the reason film and animation looks as good as it is today. Not only that, I would argue that computer graphics research is fundamentally the most important form of research for the modern computational scene that we see today everywhere, right? GPUs are graphics processing units, right? They were initially intended to do graphics, right? Like, sure, maybe there could be a world where today people start to develop whatever they would call graphics processing units, but purely for computation, with like a very similar architectural scheme and all that kind of stuff. But the fact is, all the computation happens on the GPU. Computational physics, computational chemistry, computational biology, everything happens on the GPU. Machine learning, AI, everything is on the GPU, right? Graphics, is incredibly important. And I think anybody who claims that computer graphics research is kind of a waste of time is not acknowledging the clear sign that the computer graphics research has created a literal computing like renaissance in a way. Like we're able to do much more now because the GPU, not only do we have algorithms that work on the architecture, but the architecture is fundamentally better at certain operations. You know what I mean? And you're right, visualization is easier than staring at data tables too. Like this is one of those things where like it's immediately visual, people will buy it. You know, Pixar, like for example, always puts out papers with each of their films. It's crazy. It's really cool. The repo available for the repo for right now. Yep. Fable.jl is probably the one that I'm talking about right now. So this is the So this is the rendering engine as it is. Oops, sorry about that. This is a rendering engine in Julia. There's some documentation available of how to use it. But I'm rewriting it in C++. So let me go over there, or C. So let's go to Quibble here. I'll give you the repository, even though I'm still working on, basically I have a big PR that I'm working on right now to recreate all the stuff that we have in Fable.jl. It's getting there, but this is where the future direction will be. And I'll be working on that on stream as well. So Fable.jl is the currently working version. It's just very slow for compilation speeds. And actually, even in the documentation here, I discuss why it is that I stopped developing the package. Admittedly, maybe a little bit melodramatic, but it describes exactly why I had to move away from Julia. In here, we talk about like different like general information, how to use the package, all that kind of stuff. And also we have some examples like the rotating square, which allows you to basically apply any mathematical transformation to an object. Here, the object is a square. And then we can show, oh, you can do this cool warpy thing with a square. And you get infinite resolution because of the way the rendering works. You don't have like mesh-based artifacts and stuff like that. I'm using Qt browser. Qt browser. I think that's how you spell it. Anyway, this is a ramble on top of ramble. Let's keep going. All right, that is that. All right, let's get back to this. So what was I doing? We're going to CD into projects, CESMIX, Molly. We're going to go into VI kernels, source kernels, and then we're going to go down to line 233. Okay, and what I need to do is I need to figure out what's happening here. So NBS, right, good. And now we need to do no neighborless kernel in here. So for the no neighborless kernel, I have to figure out what special means. But once I figure out what special means, I think we're good to go. The other thing is I need to figure out what's happening here. So what I was going to do is I was going to use a symmetry argument to say that we don't have to go through all the coordinates, right? We can instead just go through half the coordinates, right? But looking at this kernel, it looks like they go through all the coordinates. Oh, I see. The reason they do that is because they have a neighbor list, which uniquely identifies which particle you go through. Whereas in my case, I'm going to say we use symmetry so we don't have to go through all of them. If it's okay to ask, how is research in terms of money compared to dev industry? You're probably going to be making less as a researcher than if you were to go into software development. Just how it is. You will be making a roughly equivalent amount of money if you are a full professor to what you would be making if you are a mid-level software engineer at a high, like a FANG company, right? I mean, let's just qualify that. Average salary, physics, professor. So it seems that on average they make about $100,000 per year for a physics professor. I think computer science professor usually makes a bit more at $130,000. And again, this is just like random stuff that I found on Google. The median salary for a tenure track assistant professor in the computer science is $90K, but some make a lot less. So I reckon the estimated total pay for a computer science professor is $200,175 per year with an average salary of $135. So let's just take this one at face value. What is this? That wasn't what I meant. No, I want. What? What is this? Okay. Let's just go with what Google said, and we'll say the average is 135,000, right? Now, is that a lot? That is a lot of money. No doubt that's a lot of money. But it's not like significantly more money than you would make in industry. And keep in mind, this is at the end of your career. That's the absolute most that you can get. And so yeah, you get pension, you get other benefits. Like for example, you can't you can't get fired as easily, but also you're working a lot more than the typical software engineer, right? Because not only do you have to teach classes, you also have to manage your own research group, which means mentoring students. You have to apply for grant after grant after grant. It's a lot of work to be a professor, and I think most people don't acknowledge that the majority of your work as a professor is doing research, not doing teaching. Teaching is still there as basically an unnecessary side job that you have to do in order to keep the lights on, type of thing. So when it's put all together, you're probably not making as much money. But the advantage is that you get to do research, right? And you get to run your own research group. And for people who don't, 135,000 is a lot of money. Like you're gonna be fine with that amount of money. You know what I mean? So, and like they're saying here, I heard some professors that they do additional consulting work, right? So usually the summers you can take off as a professor, and you can instead focus on your company or something like this. And that does work as long as there's not like a conflict of interest between your company and the research you're doing. There's like a lot of, wiggle room as to what you can do, but certainly it is possible to run your own company and to also be a professor. So there's ways to top off the salary to make more. But yeah, this is like at the end game is this amount of money. Like that's as much as you could potentially make in this position, and this is the position everybody wants. Like this is what everyone is shooting for, right? And so if, it's not money that people are doing this for. They're doing it for the love of research, the love of pushing the boundary of human knowledge, and the ability to just constantly look and try to solve little problems that are interesting to them. That's what they're doing it for. It's quite different than in computer science elsewhere or companies elsewhere where the amount of money you can make actually is quite high. Like if you decide to go through a traditional track and you can find your way consistently hired up to like management positions and stuff like this, it's your highest amount of money is capped as a researcher, where it's not quite capped as much as software engineering. If you play the game right. Is what I would say. Let's see. I heard from some professors. Oh yeah. Man, I envy the energy and enthusiasm that you have for what you do. I'm a very lazy person. You say I have a lot of energy and enthusiasm, but yet I have done no work. I have written no lines of code. I've copy and pasted some stuff and modified a few letters. You know what I mean? I've done nothing today. Admittedly, I've only been streaming for an hour, but even so, in an hour, I should have done more than this. But yeah, also, I will say one thing. I personally prefer, I don't know how to put this, but I have three different types of content I put out. I do writing content, right? Like the GPU book, like the algorithm archive, the fiction book that I'm writing. I do a lot of writing because I love writing. But I also do a lot of stream work. The fact is that for me, writing and streaming are basically the two things I really like to do. Unfortunately, most people know me from the videos I put out. And don't get me wrong, I like the videos. I think the videos I put out are really good. It's just that that's the third thing that I like to do, and it's it's one of those things where most people who watch my content are coming from the videos, and I feel like the stream is better. The writing is better. The videos are just kind of there as a way to engage people that would not ordinarily watch the other content. You know what I mean? And so my point is that in terms of enthusiasm, part of that is because I'm live and I actually enjoy talking to you guys and having conversations in this way. And this is fun for me. I enjoy that. Like I've said, this particular project is to be honest, one of the most annoying software development experiences I've ever had. You know what I mean? And I don't want to have to go through it again. Even so, I have energy because I'm with you guys and we're chatting and we're kind of making fun of it and we're getting through things. You know what I mean? I put a lot of time and energy into my procrastination. That's fair. Look, I mean, you're here watching a stream about someone doing software development or pretending to do software development. I get it. Presenting stuff. Yeah, that's it. I think that everyone learns in different ways, and so it's important to have different avenues to teach. But I also acknowledge that for me personally, I find streaming content to be much better to learn from than just standalone YouTube videos. And I also find that written content for me is the best, right? And that in general kind of is where my level of enthusiasm lies, The reason I find streaming content so much better is because you can ask direct questions, and the tone is more conversational, right? It's basically second monitor content. It's there, you're listening to it in the background, and then they'll say something interesting, and then you ask a specific question about that, and then it goes back to second monitor content. And I think that's a very, it's actually very nice for the watcher. It's very nice for the viewer. Okay, let's actually get this done though. So what is special? What does that mean? So what we have to do here is we have to do two things. So one, I have to figure out why we're only adding to energy of 1. That I'm not entirely sure. I don't know why we're doing that. So let's go down to the normal potential energy kernel. And we're doing the same thing down here. We're only adding to energy of 1. So what is energy in this case? Are we calling this energy? So what was this before? So what we have PE vec no units. And we are calling that, so the potential energy vector no units. Why are we adding all the energy to just a single element here? That's what I don't understand, I don't think. Maybe I don't need to understand it. If unit of PE is not equal to E, wrong energy unit returned, that's fine. And then, yeah, it looks like all we're doing here is we're adding to the potential energy, and then we're adding that all to the first element. I guess it's fine. It's not a big deal. We'll just kind of copy this code and see if the tests work. And have like a version of this code that works. So what I need to do now is I need to figure out where potential energy GPU, what special means the potential energy GPU. Potential energy GPU, I don't think it's defined in this. I don't think it's defined in this function. I think it's defined by the user. So let me go up here and let's try looking again. So we have to do. There's a pairwise, yeah, so it's defined by the user, which is fine. That just means we have to find an example where it's defined. So let me go over here, run this, and then we're going to run grep-rl, and we're looking for potential energy GPU. Okay, and we're going to go into the VI source energy, and let's look for potential energy. All right, potential energy. In particular, potential energy GPU. Also, I do apologize. I'm still a little bit sick, guys. So like my nose is a little bit runny. I'm sure you guys are hearing it and getting really annoyed at how much I'm sniffling. I can't say anything but sorry about that. GPU. Pairwise PE GPU. What am I looking for? Potential energy GPU. That's fine, but these are completely unreadable. Great. That's perfect. Can I just grep-rl special? What does special mean? Maybe I just go to the docs and I look for special. I struggle on how much interesting stuff is available. Like things used to be much less divided. Yeah, qualify that statement. What do you mean much less divided? In terms of like finding interesting stuff was easier because people's like interests were more like singularly focused on one thing. Like, sorry. Like everybody back in the day was watching, oh, I don't know, whatever it was on YouTube. Like they all kind of watch the same content, and now it feels like everyone's watching different content. Or are you talking more like there's just, I don't know. Yeah, I don't know. Okay, so let's go here. What am I doing? I want to go to Molly, and I want to go here and go to the docs. Docs stable. And then I want to look for special. All right. Molly.force special. Let me just see if I can find. An optional argument special is a Boolean determining whether the atom pair of the interaction should be treated as special. What does that mean, though? Okay, so looks like I won't know. Special is a Boolean determining whether the atom pair interaction should be treated as special. This is specified during neighbor finder construction when simulating molecules. For example, non-bonded interaction for atoms in a 1-to-4 bonding arrangement are often weighted by a factor of 0.5. For interactions where this is relevant, special can be used to apply this weighting in the interaction. I guess then special is always going to be false for us for this particular case, is my guess. 1 second. I'm so sorry. I'm gonna be right back. I gotta blow my nose. Kaz Games, Leo's potential energy confuses me because doesn't it increase as you move away? For example, the Earth. So does that mean some object light years away has a huge potential energy? And doesn't that go into some equation like Schrodinger's equation? That's an interesting question. So what's actually happening here is that your energy is, think of it not as like, okay, you know, potential energy, yeah, it depends on your distance from an object, but think of it more as the derivative of force. Yes, it is the derivative of force, right? It's not the other way around. Force is a derivative of potential energy. I think it is the derivative of force. I think that's right. Because so if your force, right, is equal to gmm over r squared, right, which is what your force is directly related to the Earth, then you do df by dr, which ultimately means that you're going to do you're basically going to turn this into essentially a GMM over R situation with a 2 out front. 1/2, sorry. Which is your energy in this case. So what that means is as you get further and further away from the Earth, in principle, yes, R increases, right? And so your energy increases as well in this case. But the scaling is much less than it is for forces, and the rather, as you get further and further away from the Earth, the R increases, so this value actually goes down, right? And so potential energy is a function of the radius, a function of your distance from the object, like a function of the height. It's usually like G. Wait, what do people usually consider potential energy as? It's like, oh gosh, what is it typically? It's like just GH or something, like G times your height. Isn't that what people typically say it is? I don't remember. What's hard to learn? Quantum mechanics or organic chemistry? You guys, yeah, MGH is usually what they say for potential energy, right? So I'm doing something stupid here. I think this R has to come out front somehow. And what am I doing? What am I doing that's dumb? I'm doing something dumb here. I know that DFDR is going to be your energy, right? Oh gosh, guys, man, my physics is dumb. There's going to be someone in the comment section of this video getting really pissed off at me right now, and I'm so sorry, guys. Derivative of force, potential energy. No, R has a power of -1/2. R has a power of -1/2. All right, so this goes -1/2. That goes out front. Oh, right, and then you add 1, so then it's GMMR, so it should be 1. Oh, gosh. Let me just double check, because now I feel like I'm dumb. I know I'm dumb. I'm... Gosh darn it, guys. All right, so F is F is a derivative of energy. It's the other way around, guys. It's the other way around. That's... guys. Man, I am so dumb. I'm so dumb, guys. Yeah, you're right. It is the other way around. Yeah. You guys are right. I'm dumb. Okay, so it's the other way around. Du over dy is going to give you your force. So if you have the energy, you can find your forces with a derivative, and the other way is an integral. Yeah, we're relearning entry grade physics. Guys. I'm going to be right back. I got to blow my nose. I'll be right back. This is very embarrassing for me. I'll be right back. Okay, I actually see a super chat in here, which is the first time I've ever gotten a super chat. I really do appreciate that. $20 for you, basically Monopoly money. I'm out, sleep. Have a good evening, or whatever time it is your time. I really, really do appreciate that, by the way. I've never, this is the first super chat. I really do appreciate it. For the record, guys, I did enable super chats and members on YouTube, but I didn't do it on Twitch. The reason is if I enable it on Twitch, Twitch forces me to put advertisements on the stream, which I find not okay. And so I instead said, it's okay on YouTube, but not okay on Twitch. That's how I've done it. And again, I really do appreciate that. That's, that means a lot to me that you're willing to do that in the first place. It's actually kind of, I don't know. It's the first time this happened in a long time. I really do appreciate it. And I appreciate that you guys are enjoying the content enough that you're willing to do that, you know? Okay, so let's talk about this really quick, because now I've got so much egg on my face. I have a physics doctorate, guys. I used to teach this to students, and I somehow have completely forgotten everything, right? The derivative, it's usually MGH. That's what you usually do for for potential energy, right? Now, what does that mean? That means that that if we do, I know that the force is GMM over R squared. Potential energy should be something like MGH. Guys, I've completely forgotten. I forgot all of this. Let me just go back and let's just look at this really quick. I'm sorry, Kaz Games. I think a stretch spring and the larger distance, the more potential energy. I agree with that intuitively. I know what you're saying. But MGH is for when we consider a constant gravitational field. Right. And obviously that's not true if you get further away from Earth. And I think that is the intuitive solution here. As you get further away from Earth, G falls off. G is no longer the same, right? Because it's dependent on R. And instead we use the gravitational constant, right? So MGH is only works if we assume the same gravity. So that's the intuitive answer. But now I have to get the egg off my face and like relearn basic physics. What do we have here? It's really comforting to see that even with your expertise and experience, we shouldn't expect ourselves to remember everything perfectly. Yeah, okay, yeah. But this is also very embarrassing. Like, the level of embarrassment I'm feeling right now is so high because this is like, literally, I've taught this so many times, you know? It's going to be impossible to get away from AI. What do you mean AI? Oh, how's this relate to this? At least we know Laos Labs is not an AI. I forgot how to add at one point. For whatever reason, everything was multiplication at one point. No, I know exactly what you mean. Also, sometimes you do a multiplication algorithm. Like there's one, the Schoenhage-Strasset algorithm, I think is what it's called, that uses an FFT to do mid-level multiplication. And then I was on an FFT kick for a while, and like all multiplication was FFTs. And then I kind of forgot how you do a large-scale multiplication without FFTs. This happens all the time, you know what I mean? Let's see. MGH is formally considered constant gravitational force. What about action? Action as in what? What are we talking about for action? GPUs are going to be NPUs. That could be true in the near future, but the architecture for NPUs is similar enough to GPUs that like I think it's worth writing a kernel handbook so that people can start to at least use massively parallel hardware in such a way. So I think it's okay. What is harder to learn, quantum mechanics or organic chemistry? I will say I know quantum mechanics and I don't know organic chemistry. So at least from this data point, I would believe quantum mechanics is easier to learn than organic chemistry. Just because I struggled with my organic chem class, but I did quantum mechanics for a long period of time and I found it relatively intuitive at the end of the day. I'm an idiot, just for the record though. It's really comforting to see. GPUs are all going to be NPUs. Okay. Addition is just a logarithmic multiplication, so why even require addition? That's a fair point. That's a fair point. Okay, let's do it. So we have a force is GMM over R squared, right? I'm an idiot. So this is GMM over R to the 1/2 power, okay? I knew that the potential energy should be, so to do the derivative here, we're going to bring the 1/2 out front. But why am I driving this one? I should be driving the other one, right? So if the potential energy is going to be GMM over R, then that's going to be GMM R to the -1. And then we go to -2. So GMM R to -1, right? And then we do the derivative of that. And that means it's going to be negative GMM over R squared. Yes. Right? Right? That's -2. Guys, I'm so bad. This is -1. Not 1/2. What was I thinking? And then this is what happens. So there we go. That makes sense. We start with GMM over R, and then we do the derivative. We get GMM over R squared with a negative out front. That's what it is. Guys, what the heck? This is the most embarrassing moment of my life. I don't know if I can even have this stream public after this. That is so bad. Oh my goodness. I haven't done a derivative in such a long time. I forgot how to do it. My goodness. My goodness. Oh my goodness. I'm embarrassed. That's awful. Most papers I can find on Gaussian splatting incorporate AI. So the issue is that most people are using Gaussian splatting as an AI formulation. Rather, what they're using Gaussian splatting for is to do more AI stuff because it's just AI is a hot topic right now. But I would argue that it actually has more broad applications than AI specifically, and I think it can be used as a general purpose rendering, and that's actually something that I'm doing with the work that I'm doing right now. Memorization scared me away from organic chem, but that stuff comes up all the time, it seems. Meds, fossil fuels, right? Actually, all of them except wiki. Don't sweat it. You're lucky we also don't know how to do that. Yeah, maybe. Guys, I'm so sorry. That was awful. That was awful. It is, but fine, we got there. We got there in the end. What I was trying to say is I think exactly what someone else said earlier. What I'm calculating here is basically G, right? The value for g, which is not equal to 9.81 in all cases, right? And so when you're talking about like having a super high potential energy because you're very far away from Earth, what you're actually doing is the following. So journal, new page before, we have this graph of what the of what your potential energy looks like as you go away. So like on Earth, it's like 9.81, and then it goes down and down and down and down and down, right? And so what ends up happening is this trails down to 0, which all the way down to 0, right? And so your potential energy is not actually just mgh, it's the integration of this curve. That's what I was trying to say, right? And so eventually this tapers down to roughly 0, and like you get negligible benefits from being that far away from Earth. That was what I was trying to say, but it did not come across, and I forgot how to do a derivative, and it's very embarrassing, very, very embarrassing. If you feel that you're banging your head against a wall, take a good break, step away. Stepping back, you will see a path around the wall. That is correct. I'm so sorry. It is because the potential energy decreases as we get further away. That's what I was trying to argue, which logically makes sense physically, but I could not express that because I forgot everything. So that's embarrassing. But yeah, look, I really appreciate you guys sticking with me, even though I said some really dumb stuff just then. Okay, so let's get this code written. The issue that I'm struggling with right now is figuring out what this particular function is actually trying to do for this kernel, right? So I copied it from somewhere else, and essentially we have coordinates and velocities. We have a vector, which is basically telling us we have 2 points in space, and we're trying to find the vector that connects them, like the direction and the magnitude of the force, right? So basically the vector gives us that direction, like, you know, these two particles are like this distance away, right? Okay, good. Then we do potential energy GPU. We have the integers of 1. This again is just taking integers of 1, which is interesting to me because I would personally think, I don't know why we're just doing 1 here. dr atoms of I, atoms of j, special, coordinate j, coordinate I. So why are we only doing integers of 1? Let's go look at the other kernel and see if we can figure that out. So inter I, what is integers in this case? Integers is here. Integers of 1, what does integers mean in this case? I thought integers was, this could be the number of interactions that we're working with. So we only have 1 interaction, and therefore we're just calling that first interaction. I guess that's fine. Like, it could be we have different force interactions that we could call different ones. Fine, I guess it's okay. So we have dr, which is going to be the kind of like distance or the direction that we're going in. We have atoms I, atoms j, e, special, coordinate I, coordinate j, boundary, velocity, velocity I. That's all fine. And then it says for the interactions in interest 2 through n, we add to the potential energy all the other interactions. There we go. dr, atom, that seems fine to me. This is all okay, I think. And then once we've done all of that, then what we do is we say we add to energy 1 the u strip of PE. I don't know why we're only adding to energy 1. In my mind, we would be adding to like all the energies. Like each particle should have its own energy. But maybe I'm misunderstanding. Maybe this is explicitly a summation, and that's what we're doing. I don't know. But increases as you move away up to a point, and then it decreases. Makes sense now. Like a spring, as you stretch it, the potential energy increases until you go too far, and it's all stretched out. Right? Aren't there 2 0 points of PE at both the 0 and the infinite distances? That is true, actually. Yeah, that is true, because 0 and, well, the problem is that this is one of those things that as you get closer and closer to, yeah, I drew this graph wrong, right? Technically, this is not 0. This would be the radius of Earth, and there is a 0 back here, right? And that 0, this kind of just goes up, 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 and eventually it's like infinite until you basically hit the very center of Earth. But the problem here is that because this is not a constant, like the Earth is not a point particle, you then have to keep in mind that the mass that you're pulling off of, right, it will end up being that the mass drops down, and so we'll end up doing something like, I don't know, something like this in terms of the actual potential energy, right? And so yeah, you're right. It depends on how you treat the Earth. If you treat it like a point particle, then it explodes past when you like go inside the radius. This is actually why when people do like these types of simulations, they do F is equal to gmm over r plus 1 squared for the force, and they add a plus 1 in there so that no matter how close you get to the point in space, you will never go below 1, so you never have to deal with this explosion up here, right? But in actuality, right, if you were actually going deep within the Earth's core, then it would drop down to 0. Yeah. Yeah, this is one of my, this is a very good paper that came out a while ago. It was the one that popularized Gaussian splatting. Before that, like, people knew that splatting methods were like useful, but that was the one that said, yo, this is why we should use it in the future, right? Similar to ball uniform charge, only the charge, the only charge that matters is below you. Right. It's the same thing here. This is the thing about physics. Like, a lot of these formulations, they just rhyme with each other. They're basically the same with small constant differences. And so if you know gravity, then you know, like, electrostatics, and you know, you can kind of use this knowledge anywhere else. You know, I, however, have forgotten everything, and I feel very embarrassed about that. All right, let's keep going. So I have a few questions as to what this is doing, but I think this should at least run, and we can start to test it again. So let's go back over here, and let me just run test. In fact, let me just do pre-compile, just to make sure I didn't have like a typo or something. And then we'll run the tests as well. It should run, I think. And then we can see what the error is, and then we'll try to figure out like what the kernel is actually supposed to look like. And in particular, I'm just going to ask Joe about this. I'm going to be like, hey, what is this actually supposed to be? And I might just commit this and be like, I actually don't know what this is supposed to do. And I don't know why we're adding to just 1 in here. I just be like, I'm sorry. I love Gaussian splatting, but my current implementation has a bug somewhere. And it's, yeah, I understand that. I mean, because you basically have to implement your own software rendering approach, right? And software rendering sucks. I mean, like, you have to do everything, like, as much as I don't like the traditional graphics pipeline that you have, like, you know, vertex shaders and fragment shaders and potentially mesh shaders or geometry shaders, and it's kind of all over the place, what it does do is allow programmers to more easily think about like what's happening at certain stages of the pipeline, and it hides away a lot of the complexity that you would have to implement on your own if you're doing some sort of software rendering approach. How do you think adding flexibility to solid objects in physics graphics do possible? Wait, how do you think adding flexibility to solid objects in physics graphics do possible? Okay. You're asking if you want to change a hard body into a soft body, I think is what you're asking, right? Like, so you have like a billiard ball and you want to turn that into a bouncy ball, I think is what you're asking. So the answer is actually that this is simultaneously difficult and not difficult depending on what engine you're using that I'm aware of, right? Because keep in mind, journal new page before, this ball representation is not a ball, right? It's already represented as a mesh, right? It's just a bunch of triangles that I'm not going to be able to draw, but you know what I'm trying to say, that are basically drawing this ball, right? And so at the end of the day, right, vertices with springs, right? That's what it is. You already have discretized the outside of the ball in order for it to fit into your graphics framework. And so you have a good starting point to start mimicking the behavior of, like, for example, a tennis ball. If it hits a wall, right, it goes something, instead of hitting the wall and just being a circle, it hits the wall and kind of smushes against the wall, right? And so you can start to do like a real simulation off of some sort of mesh. Now, I think in order to do it perfectly physically, you have to do a simulation that takes into account like the inner 3D-ness of the simulation, and then you go from there. How do you get rid of the mesh? That's a very interesting question, right? Because actually, I think almost all of these methods that are going to do soft body sims are necessarily on meshes. They're like finite element methods or something like this. There are ways around this. You could do finite difference methods, which would basically, you know, treat the ball as a fluid or something like this, and then you kind of simulate the movement without manipulating the mesh. Then you could do what I'm doing, which is to do an iterative function system approach, which is to say that we have a ball, and this is actually a point cloud of individual points that are determined based on like an underlying equation to create the ball. And then you give it the analytical formalism to what you would expect it to transform into, right? And so it hits this wall, right? And we know physically that it should be warping via like, I don't know, like maybe the warping function is going to be equal to f is equal to like 1/2 x or something like this. You know what I mean? And so it just will squeeze and then it bumps back out or something. And so like you can create an analytical formalism that allows you to express that soft bodiness, which is something that I can uniquely do in the engine that I'm working on, which would get you away from meshes. Is it possible to optimize the simulation by using less grid points to interpolate between the points and not suffer? It depends on what you mean by suffer, right? So the higher resolution, the more physically accurate the simulation should be. The bigger the mesh, the more points the mesh has, the more physically accurate that mesh should be. But yeah, I mean, like what Hanif is saying here, points and joints should be good enough, and it will be good enough for most cases. It's just if you want, there are certain cases where because you're limited to what a mesh geometry can output, you're also limited to what you can express in like a vertex shader or something like this. And sometimes the vertex shader is not as robust as you want it to be, right? And it might be better just to write down the math you want to do. And so there are different situations where you might want different solutions here. Balls under gravity, at least changing the form of some if forces and maybe done in parallel. Repeat that. I didn't catch that. So you already have the cinematic of the phenomenon modeled, understood. What do you mean? Sorry about that. Core is not defined. This is going to be on line 232. Backend type of sys.chords. All right, let's try that again. I really should just be running this specific test instead of like running all the tests over again, but I don't care. I mean, the point cloud method you say you're working with. Oh, right. So in this case, the assumption is that you have already a formalism that allows you to model that movement, right? So rather than treating it as a bunch of vertices on the mesh, the idea is you... Sorry, I'm so sorry. The idea is that you write down mathematically what the transformation would look like for the points in space. It doesn't work for all cases, right? And this is a particular case where like you might have to eyeball some things and it might not, like you have to consider what the rest of the particles are doing and stuff like that, so you have an idea. Like, here's what I would actually do if I was doing it in the method that I'm talking about, right? We have a ball, right? This ball has particles inside of it, right? Here's a particle inside of it. The ball has some sort of density, right? And so we have the radius here, r. And this density basically says, look, particles are not allowed to exit this mesh. They must stay in, or exit this ball domain. They must stay within inside of it. And so it gives you some sort of like perspective on what will happen when it hits this wall. And you know that r is going to shrink, and you know it's going to shrink in a particular dimension based on the angle of this wall. And then if you know like what's going to happen, because it's going to hit the wall at this particular angle, that means you can basically simulate the movement of these particles based on where it lies on this circle, and which should give you the ability to, like, you know, like based on the density and a bunch of other things, you can find a way to model this, right? It depends on what you want to look at, right? But it should be very similar to what you'd already be doing for soft bodies with vertices. I think the vertex shader should be almost identical to what you'd be doing in the other way. It's just that you write it down, you just write down the vertex shader. And in this case, you write down what would be a like a transformation of the ball. And it's like, it just allows you to move the points in basically a very similar fashion. I'm not doing a very good job of describing this because I have not actually done this. I'm just guessing at what it would look like. The main thing is you can be more specific about certain interactions, is what I'm trying to say. If we smash a ball in a few directions, it would deform based on every action separately but simultaneously. If we smash a ball in a few directions, it would deform based on every action separately but simultaneously. Yes, I think I know what you're trying to say. So if you hit it with two hammers at the same time, you would have to then find some way to like figure out like what that would look like. But you'd have to basically propagate a shock through the system. And I think that's the issue here. We're asking, how do we simulate shocks, right? And when you think about it like that, there's actually a lot of literature in terms of how to do those simulations, both for like hydrocodes, for finite element methods, for all these different things, right? And so it's quite, it's very well sussed out, right? No method of length and nothing. So I think this is what I need to do. If type of NVS is equal to, I just need to put nothing in here. All right, I'm gonna write this, and we're gonna see if that runs. And then I think I'm just gonna push this. I'm gonna ask Joe what to do. Yeah, I'm gonna ask Joe what to do at that point. I think that might be where I have to call it for today. It's just a little unfortunate. I remember we didn't get into what actually happens in terms of the actual collision and temporary deformation. We just had some sort of energy momentum conservation before and after pictures. Yeah, so it depends. Like, it depends on how soft you are. It's like how soft the soft body is. Like for like billiard ball interactions, it's very easy just to write it down. But for soft body like simulations, it becomes a lot harder because it's very difficult to predict like what every element in the mesh is going to transform into. And so you really have to think about like a lot of different things when you're doing that. I don't doubt that there are graphics engines that allow you just to write down, like, I don't know, the energy or momentum of the particle, like the positions, and just do all that simulation for you. But it's not entirely obvious what, like, if you're looking at it from just like pen and paper, what you would have to write down to like simulate the movement of a vertex, as it corresponds to all the other vertices. I think it's something like the n-body simulation that we have written down here, where you have like some force that's dependent on all the other particles in the simulation, and it's just, yeah, you have to think about it a bit. You need like 3D form of density to make calculations correct, right? Exactly. And so I do wonder if there's a way to take the 2D mesh that we already have for the sphere and to transform that into something that replicates the 3D form. I don't know. There's a lot of questions, right? I don't actually know. I don't know. I never actually did soft bodies. I just kind of am vaguely waving my hand away at what I think it is, you know? So anyway, let me get some water. Sorry. Yeah, there are a lot of questions about the rendering engine that I'm currently working on as to what we can actually do with things represented as a point cloud. Atoms not defined. What is this? Why do I keep getting these not defined? I just want it to run. That's it. I just want it to run. So 234 here. Length of atoms. That's because we don't have atoms. We need to do a length of sys coordinates. And then we go down here, length of NBS, that's fine. Pairwise GPU should be fine. Let's test it again. As long as it runs, I'm gonna go ahead and as long as it runs, I'm gonna go ahead and submit it. Say, Joe, this is where I'm at. I don't know if this energy kernel is correct. I don't know what it's actually supposed to do. Could you just tell me? Because it's weird that it's all summing to 1. I don't know. I find that a little bit weird. User case is if only that a way of good approximation of integrals, right? Yeah, I think, yeah. Like there's a lot of things that modern computer graphics methods can't do particularly well, like density rendering, like the rendering of like clouds and stuff like this. Is actually Gaussian splatting is pretty good at this, which is why I think it's such a big deal. But when you think about it, like the majority of the stuff that we interact with are 3D volumes, you know what I mean? With some sort of density associated with that, like with that object, right? And so as you start to see light like filter through, I don't know, the clouds or like fog or something like this, or even like tree leaves or something like that, there's some level of like, you know, translucency that you have to take into account. And it's like just, it's hard to get that in like mesh-based approaches and stuff like that. So what I don't get with Gaussian splatting is how to deal with transparency. Oh, actually, I thought it came naturally. I thought it came naturally because you can treat the object as a, like, you know, like we have object 1. Let's say we have a ball here. It's a 3D density. You know, I don't know why I'm saying, but you know what I mean. It's 3D density. And then essentially you throw that to screen, right? And based on the density of the points here, like because it's a sphere, you would see a density distribution that looks something like, well, probably more like this, right? Because it's a sphere. And then you just say, okay, well, this is, you know, alpha is equal to 1, and this is alpha equals 0. You know what I'm saying? So like based on the density of the points that have coalesced onto screen, you know what I mean? It feels like it should come naturally to also change the density, like, or change the opacity and transparency. I feel, but maybe I'm wrong. Energy units not defined. All right. Value of energy units, value potential energy GPU. So what's not defined? Energy units is not defined. It says it's not defined on what line? 236. There. So it is here. Value of energy units not defined. But that's because we don't have energy units. So that means I need to go back to my code and see what this is actually supposed to be. That's okay. Let's go here to kernel abstraction support. Here we are. Go to source, go to kernels. Where are we? Kernels. And then we go to line 233. Where are we? 233 should be right here. And what was it reading? Value of energy units was right here. So where are energy units defined? Yeah, where are energy units defined? Well, let's just look. So here's value of energy units. We look for energy units. All right. And we want specific PE GPU. Let's go back to line 233. That's the only time it's used in this kernel. Well, that means this kernel is just wrong, isn't it? That's okay. What are we trying to read in here? Value of E, where E. That is unfortunate. That was probably removed in the code. So let's take a look at the force kernel then. Pairwise force no neighborless. Pairwise force GPU. And what do we have here? Value of D, where D is what? D is read in from system DAT. And value of force units, which is, where's force units come from? Where does that come from? Value of force units. Energy units, and then force units. Does this code just not work? Value of force units. No, it's being read into specific force GPU. I see. And so if we go here as well, then we do value of force. No, but it's not being read in for pairwise force GPU. Oh, come on, you're kidding me. Oh, this is such a pain in the butt. This is such a pain in the butt. What do we do for these vowels? I don't know. Easier cases. Does optics based on density of cloud? Is that Julia? So the optics, so in this case, the transparency would be based on the density of the cloud, yes. Because the formula for transparency is order dependent. So rendering object 1 first or object 2 first will result in different blending. That's part of the reason game engines don't like partial transparency, because it has to sort through which triangle is in front of the other. So what I do in my engine is the following. I actually give each object a priority based on where it is in I give each object a priority based on where it is in space, like from the viewer or something like that. And then as it's splatting to screen, I take that priority into account for blending, right? So this would mean like if you have a transparent object in front of a non-transparent object, we deal with that priority separately at the time that it's rendered to screen. That's how I deal with it. The other thing I do, or I'm planning to do, is add in some AD in there, or something like AD, so that we don't deal with points. Like if this is occluded, then we just don't render this section of the sphere, right? Which we can do by seeing the intersection between like one object and the other object, and then creating a transformation to basically push the points out of this region, if that happens to occur. And so what I'm actually like kind of messing around with the fact that these points can be represented, or the transformation of these points can be represented as an analytical formalism, or can be represented analytically, to enable me to just push the points away where they need to go, so that we interact. We do not get these weird interaction cases as often, is what I'm doing right now. And again, they all have a priority so that they're added together correctly at the end of the day. Yeah, that's what I do right now. It's not necessarily the most elegant solution, but I'm not necessarily trying to do the most elegant solution. I'm trying to do a solution that works, and that can give me fast results, and that I can create good results with for like the initial tests and stuff. So, and I think that's kind of where we're at with Gaussian splatting, where it's not very clear what, it's not very clear how it's going to shake up the industry just yet. So here's what I'm going to do. I think I'm going to go ahead and push this. I'm just going to mention the things that I don't know to Joe right now. So let's go ahead and do git status, git add source kernels, git status again, git push origin ka support. And I'm just going to say, this is what I don't really understand. And I'm just going to say, okay, I forgot to commit. Small changes, still broken. Git push origin ka support. All right. I don't know if I said, but yes, this is Julia. So let me go over here, kernel abstraction support right now, and let me just mention the things that I'm a little bit confused about. Okay, so a few notes. One, let's see. I am still not sure what the PE kernel should look like, but I've copied from let's see, from the neighbor list implementation, and wrote this. Again, I don't know what this is supposed to look like. This is me just being an idiot. Vi source kernels, and then we're going to do pairwise PE kernel no neighbor list here. And let's grab this. Where is it? Pairwise PE kernel. Where are we? Here, I believe it is. There we go. Grab that. Paste it over here. I guess I don't understand why it is adding to energy of 1. Shouldn't it be adding to energy of I? This could also be a typo I have in the, let's see, what's the other function called here? This guy. Without, with a neighbor list. Okay, the other thing, is I'm not sure what val, where are we here? Val of energy units is supposed to be. Okay, so I'm not sure what this is supposed to be here. Function arguments for pairwise PE GPU. Okay. One second. Pairwise force GPU. There we go. Something like this. Okay, so that's I didn't do much today. I'm so sorry. I'm gonna go ahead and comment that and just say, look, I don't actually know what's going on here. I just have a few quick. I think I need to actually just call this person and be like, look, I don't really understand what we need to do to get this fixed, and we need to go from there. I heard in 2D engines there is a problem of floats, small offsets which make occur to the object don't move because it's stuck in a little angle on the surface. Yeah, there are some like little, yeah, that definitely happens, right? Where there's like some floating point precision issue that causes like some weird interaction. I think for any engine that happens. Is it okay reading code as part of debugging? Yeah, I don't understand why this is doing that. And I don't understand why this is no longer a function argument. That's kind of what I'm trying to figure out. So I think I need to call it here and just ask what Joe is trying to do. That's okay. The problem was, the thing that's annoying about this, and I said this at the start of stream, is the code was working. It was ready to go. We had everything ready as of, let me see if I can go back in time really quick. We had everything ready as of December 23rd, 2024. That's like, okay, a month ago now, but we had it already. It was good. We had it. It was working. And then somehow it just wasn't merged, and now it's broken again. And this is the consistent story of this code base, where it's like, I consistently try to get something done, and then it consistently breaks, and I don't know what to do about that. That's where I'm at. That's why the YouTube video it says my most recent failure, or whatever it says, because I am just stumped here. And the other thing, like I said before, this isn't an active research project. It's more of a software engineering project. And don't get me wrong, I don't mind doing software engineering as it pertains to doing more research. But one of the core problems here is that like I have not been getting research out for the past couple of years, and it's one of those things that I didn't realize was so influential for my daily life. Like I thought to myself, oh, it'd be fine if I just did software engineering. I've got a really good background. I really don't mind doing software engineering. But I've realized that like software engineering is quite different than research. You know what I mean? Like research, there's always like a feeling in the back of your mind or a feeling in your gut that like you're doing something people haven't done before. You know it's challenging. You know it's hard to do. But it's itself already like kind of satisfying. You know what I mean? Like you feel like the fact that you're doing this and no one's ever done this before, you're exploring curiosity. You don't mind if you're making less money because like you're doing stuff that again has not been done before, that is just like very unique and stuff like that. But when it comes to software engineering, like this is stuff that needs to be done. I understand it needs to be done, and it needs to be done to have research be done. But I'm not actively doing the research projects. You know what I mean? And that's very different. Not actively doing the research projects means that like I don't have an end goal here. Like kind of I'm just doing this thing, but there's not a paper coming out. There's not like something novel that's being done. There's not like I'm not pushing the boundary of human knowledge. You know what I mean? Like, and it's fine. You know, I guess I'm getting paid to do it to some extent, you know, not as much as I feel like maybe I should be asking for, but you know, I'm getting paid to do it and that's fine. But it's like, man, what a situation. You know what I mean? Like, I feel like I should be, I want to do more research is what I'm trying to say. More stuff that's boundary pushing, you know? Let's see. My head's also a bit confused. Bloody Joe, Flaming Galah. All right, guys, I think this is what I'm going to call it for today. I think it's 2 hours streaming, something like that, which, okay, admittedly is not long for a Twitch stream, but considering most people are going to be watching this as a VOD, I think this is a good place to stop. Thank you guys so much for like hanging out, chatting, all that kind of stuff. I really do appreciate it. And Alf, thank you so much for the super chat before I really appreciate it. Like I really do. This is where I'll call it for now. If you guys have any questions, comments, concerns, ideas, anything like that, feel free to let me know, and I will totally address it as soon as I see it, wherever you happen to post it. If that happens to be on Discord, that's great. If it happens to be in the YouTube channel, on the comment section, that's great. Do whatever you need to do. I'll see you guys hopefully on Monday, where we finish up the next chapter of the GPU book. I'm really excited to see where it's going, and I think it's gonna be really good. I think you guys are really going to like this next chapter. It's the first time that people will be able to like actively see the power of their GPU. I've got a pretty good example to show that power off. It's great. I'm a big fan of this chapter. And then after that, we'll start to do like real development for like, you know, basically the accumulate function, or rather summation is the next chapter. And we have like a whole bunch of other examples that we'll be going through. And so my expectation is, as we start ramping this stuff up, you'll be seeing more and more like kind of videos of me just kind of like testing out some code, doing summation, putting stuff together, like, you know, just I'll be doing more streams to just kind of work out the kinks in the code and to make it look pretty and all this kind of stuff. So you'll be seeing stuff from me. Keep in mind that for the next few months, it's not so much research. It's more just like writing the GPU book and kind of getting ready to do research in the future. And then hopefully once the book is done, should be done in like March, maybe April at the latest. We're going to hop into some real computer graphics research, and I'm super excited for this, guys. It's going to be a blast. I'm really excited. And I'm really hoping that people will stick along for the ride, and we'll be able to learn a lot together and all that kind of stuff. So that's it for now. Thank you guys so much for coming in. Have a wonderful day, night, afternoon, morning, evening, whatever time it happens to be your time. And I'll see you guys around next time for the next episode of Leos Labs. Bye, guys.